In the silent depths of space, far beyond the reach of our most powerful telescopes, a dark mystery may be lurking, a hidden star, a silent twin to our Sun, known only by its whispered name, Nemesis. Believed by some scientists to be the unseen force behind Earth's mass extinction events, Nemesis is a theoretical companion that could disturb the outer edges of our solar system, sending waves of deadly comets toward our planet every 26 million years. Though never directly observed, the possibility of its existence has haunted astronomers and paleontologists alike, blurring the line between science and cosmic myth. What if the deadliest enemy Earth has ever known isn't a supervolcano or asteroid, but a star quietly circling us in the dark? But before we continue, subscribe to the channel so you don't miss out on any of these videos. The origin of the Nemesis theory can be traced back to a chilling pattern observed in Earth's fossil record. In the 1980s, paleontologists David Ropp and Jack Sepkoski published a study analyzing extinction events over the past 250 million years. What they found was both startling and sinister. Mass extinctions, including the one that wiped out the dinosaurs, didn't seem to happen randomly. Instead, they appeared to occur with a regular frequency, roughly every 26 million years. This periodicity raised eyebrows. Extinction was no longer just the chaotic byproduct of volcanic eruptions or asteroid impacts. It looked eerily regular, as if something was triggering these die-offs like clockwork. The search for a cosmic culprit began. Enter the Nemesis hypothesis. Proposed in 1984 by physicists Richard Muller, Pete Hutt, and Mark Davis, the idea was both elegant and unnerving. What if our Sun had a dark companion? A star, possibly a red or brown dwarf, orbiting at a distance so vast and so slow that it would take tens of millions of years to complete just one revolution. During each orbit, it would periodically pass through the Oort Cloud, the vast shell of icy debris surrounding our solar system, and disturb it. The gravitational nudges from Nemesis would send a storm of comets hurtling toward the inner solar system. Some of those icy missiles would hit Earth, causing catastrophic impacts and triggering mass extinctions. The name Nemesis was chosen carefully. In Greek mythology, Nemesis was the goddess of retribution, a divine force of vengeance that punished arrogance and hubris. The idea of a star that brings death every few million years fit that image perfectly. Nemesis, the silent killer, was born. But the power of this hypothesis lies not just in its chilling narrative, but in how compellingly it stitches together various threads of astronomical and geological evidence. For example, impact craters on Earth, those scars left by celestial collisions, also seem to show periodic patterns. Some researchers noticed that certain craters, like Chicxulub, the one linked to the dinosaur extinction, matched the proposed 26 million year interval. This offered a tantalizing clue. If these impacts were not random, something had to be causing them. And it wasn't just craters. Even long-period comets, those that take hundreds of thousands or even millions of years to orbit the Sun, seemed to hint at a possible external trigger. Their orbits suggested they were being perturbed from the outer solar system. But by what? Now here's where things get even stranger. The outer solar system is not a well-lit place. It's cold, dark, and vast. If Nemesis existed, it would likely be a red dwarf or brown dwarf. These are small, faint stars that emit very little visible light, making them extremely difficult to detect with telescopes. A brown dwarf, in particular, is a sort of failed star. It has mass somewhere between that of a large planet and a small star, but not enough to ignite hydrogen fusion at its core. This means Nemesis could be lurking in the cosmic shadows, completely invisible to most surveys, unless we know exactly where to look. For decades, astronomers searched for Nemesis. Infrared surveys, like the IRAS mission in 1983 and later the more powerful WISE, Wide Field Infrared Survey Explorer, in 2010, scanned the sky in the infrared spectrum, the best way to detect cold, dim objects. But they found nothing conclusive. No sign of a companion star at the distances predicted. Did this mean Nemesis didn't exist? Not necessarily. The lack of evidence wasn't quite evidence of absence, especially when you consider the vastness of space and how hard it is to detect such an object. Still, the silence from the void began to challenge the theory. Other scientists suggested alternative explanations for the extinction periodicity. Could gravitational oscillations of the solar system through the galactic plane be to blame? As the solar system moves up and down through the dense midplane of the Milky Way, it might pass through regions filled with interstellar matter or gravitational disturbances. These could potentially dislodge comets from the Oort Cloud in a similar way. Others turn to galactic tidal forces, nearby supernovae, or even the influence of other large planets like Jupiter and Saturn as potential comet stirrers. Still, none of these models provided as clean or compelling a mechanism as Nemesis, though they didn't require the introduction of a hypothetical object no one had seen. Then came a curious twist, the discovery of Sedna in 2003. Sedna is a distant, icy object that follows a bizarre, elongated orbit in the far reaches of our solar system, far beyond the Kuiper belt. Its orbit is so strange that it can't easily be explained by the gravitational influence of the known planets. This discovery renewed interest in the idea that there might be a massive, unseen object lurking in the outer solar system. Not necessarily Nemesis, but perhaps something similar. Maybe not a dark star, but a massive planet, something now famously called Planet 9. Planet 9, proposed by Mike Brown and Konstantin Batygin in 2016, is a hypothetical planet several times the mass of Earth, orbiting the Sun at a vast distance. Like Nemesis, it would be difficult to detect directly, but its gravitational fingerprints might be visible in the orbits of distant trans-Neptunian objects like Sedna. While Planet 9 is not the same as Nemesis, it's not a star, and it wouldn't cause periodic comet showers, it does underscore a critical point. There are still massive, unseen objects in our solar system that could be hiding in plain sight. This realization forces us to confront the limitations of our observations. Our telescopes have come a long way, but the outer solar system remains a largely uncharted wilderness. Nemesis may not be detectable with current instruments, especially if it is a cold brown dwarf cloaked in darkness. If it exists, it could still be out there, orbiting the Sun with a period of 26 million years, its passage marked not by light, but by death. The implications are staggering. If Nemesis exists, it would be the ultimate cosmic predator, a bringer of mass extinctions, responsible for erasing countless species from Earth's history. Its influence would be subtle, indirect, working not through heat or radiation, but gravity. With a simple pass through the Oort Cloud, it could redirect millions of frozen projectiles toward the inner solar system. Most would miss, but some would hit. And when they do, the results would be apocalyptic. Of course, we can't talk about Nemesis without addressing the skepticism. Science thrives on doubt, and many astronomers rightly point out that the fossil record is messy. The 26 million year pattern may be statistical noise, not a genuine periodicity. Others argue that impact craters are often buried, eroded, or hard to date precisely, making patterns difficult to verify. Yet the allure of Nemesis persists. It's not just the idea of a hidden star, it's the unsettling notion that our fate may be periodically sealed by forces completely beyond our control. The hypothesis is terrifying because it makes extinction not an accident, but a certainty, repeating itself like a heartbeat over geological time. And while we may not yet have definitive proof of Nemesis, the search continues. Future infrared telescopes, more sensitive sky surveys, and refined orbital models may yet uncover something in the cosmic dark. Maybe it won't be Nemesis. Maybe it will be something stranger. But if there's one lesson from this mystery, it's this: the cosmos is not a tame place. There are predators in the dark. Some we know, some we imagine, and some we may one day find. Even as scientific doubt tempered the enthusiasm for the Nemesis hypothesis, the cultural and philosophical implications took on a life of their own. The idea that our solar system might not be a quiet, self-contained family of planets, but rather a dynamic, gravitationally entangled system with hidden killers at the fringe is something that profoundly challenges our perception of cosmic safety. The universe, as it turns out, might be more haunted than we think, not by ghosts, but by cold, invisible objects with the power to rewrite biological history. Let's go deeper into what Nemesis would actually be, if it existed. Astronomers hypothesize that it would most likely be either a red dwarf or a brown dwarf. These types of stars are extremely common in the galaxy. Red dwarfs in particular may make up more than 70% of all stars in the Milky Way. They are small, cool, and dim, emitting mostly in the infrared. Brown dwarfs, on the other hand, sit in a strange in-between category. They are too massive to be called planets, yet not massive enough to sustain nuclear fusion like true stars. As such, brown dwarfs emit very little light and are nearly invisible without specialized instruments. If Nemesis were a brown dwarf, it could very easily have evaded detection, especially if it were orbiting at tens of thousands of astronomical units (AU) from the Sun. To put that in perspective, Pluto, which orbits at an average of about $39, is already a dot in our most powerful telescopes. The hypothetical distance of Nemesis has been estimated between 50,000 and 100,000 Australian dollars. That's over a light year away, close enough to still be in a loose solar orbit, but far enough to be extraordinarily difficult to observe. At that distance, even a red dwarf would appear as little more than a moving dot of infrared radiation. So while searches like the WISE mission haven't turned up anything definitive, they also haven't ruled out all possibilities, particularly if Nemesis is extremely dim and cold. Let's explore another fascinating angle. What if Nemesis did exist, but its orbit was unstable or decaying? Over hundreds of millions of years, gravitational interactions with other stars passing through the galactic neighborhood could slowly alter its trajectory. If Nemesis was once in a regular orbit but became destabilized, it could have either moved too far away to affect the Oort Cloud or been ejected entirely from the solar system. It could even have collided with or been captured by another passing stellar object. The result? A periodic mass extinction pattern that simply stopped at some point, a silent farewell from a cosmic executioner that has since vanished. This could explain why the extinction periodicity pattern seems to weaken in the more recent fossil record. The last known major extinction, the one that ended the age of the dinosaurs 66 million years ago, fits into the pattern. But after that? Not as clearly. Could it be that Nemesis was once a player in our solar drama, but has since exited the stage? Or perhaps Nemesis is still out there, but its passage is long overdue. If its orbit is more elliptical than circular, the timing between its passes could vary significantly. Some orbits might take 24 million years, others 30 million. The average could still be 26 million, but individual intervals might appear irregular, just enough to muddy the statistical waters. Another intriguing hypothesis is that Nemesis might not be alone. Binary star systems are extremely common. About half of all stars in our galaxy are in binary or multiple star systems. That raises a philosophical question: is our solar system the exception? Or are we simply missing the evidence of our own binary nature? This opens the door to the idea that maybe Nemesis isn't the only object out there. Maybe our Sun once formed alongside multiple stellar siblings, and Nemesis is simply the one that remained gravitationally bound. The rest might have drifted away early in the solar system's formation. If Nemesis is real, then the solar system isn't just a singular star with planets. It's a binary, or once was, something we see across the cosmos, yet have long denied about our own cosmic backyard. The psychological implications are also worth contemplating. Nemesis introduces a profound tension between human self-determination and cosmic inevitability. For much of modern history, we've embraced the idea that we control our destiny through technology, knowledge, and will. But if mass extinctions are programmed into the solar system, if an invisible star is orchestrating waves of destruction every few dozen million years, then we must face the terrifying possibility that some events are simply out of our control. That, no matter how advanced we become, the cosmos holds cards we haven't seen, and perhaps never will. Now let's move into the broader framework of cosmic extinction. Nemesis might just be one potential mechanism. But what makes it so alluring is that it provides a structured explanation, a periodic event that fits the data better than many stochastic or random models. Other mechanisms, such as massive volcanic outpourings like the Deccan Traps or Siberian Traps, are certainly capable of global ecological collapse. Similarly, Gamma-ray bursts and nearby supernovae can also cause mass extinction through radiation or atmospheric disruption. But these events are random. Nemesis, if real, adds a rhythm to extinction. It transforms random chaos into cosmic choreography. Interestingly, some models suggest that every time Nemesis passes close to the Oort Cloud, it could dislodge hundreds of millions of comets. Most of these would either be ejected from the solar system or drift harmlessly. But a small percentage could be sent inward, toward us. The bombardment would last millions of years, not days or weeks. Earth wouldn't just be hit once, it could experience a drawn-out reign of destruction, creating a series of extinction pulses that stretch across geologic time. Some species might go extinct early in the bombardment. Others might vanish as the secondary and tertiary impacts change the global climate. The Oort Cloud, Nemesis's supposed playground, is itself a mystery. No one has ever observed it directly. It's believed to be a spherical shell of icy bodies surrounding the solar system, extending from about 2,000 to 100,000 Australian dollars from the Sun. These frozen remnants are leftovers from the solar system's formation, comets waiting to be stirred from slumber. The gravitational influence of Nemesis could act like a spoon in a bowl of marbles, sending countless bodies flying off in random directions. Earth, caught in the inner solar system, would be a sitting duck. Here's another tantalizing idea. What if some of Earth's water, or even life itself, was delivered by one of these Nemesis-triggered cometary bombardments? The idea of panspermia, where life's building blocks, or life itself, could be transported via comets or asteroids, has gained traction in astrobiology. If Nemesis periodically disrupted the Oort Cloud, it wouldn't just be an agent of extinction, it might also be an agent of genesis. In this strange, poetic balance, the same force that causes destruction might also bring the seeds of renewal. Nemesis could be a cosmic gardener as much as a destroyer. But despite decades of searching, no conclusive proof of Nemesis has been found. Astronomers continue to refine their models, analyze orbital dynamics of distant solar system objects, and search infrared sky maps for any sign of an undiscovered companion. The rise of data from Gaia, a European Space Agency mission mapping billions of stars with unprecedented precision, could one day help answer the question definitively. Gaia may be able to track minute motions in nearby stars or comets that betray the influence of a dark, distant object. If Nemesis exists, Gaia may yet uncover its signature. And even if Nemesis is ultimately disproven, the journey it sparked is worth celebrating. It's a story that blends astronomy, geology, mythology, and existential fear into a single breathtaking concept. It reminds us that science is a process, a willingness to follow patterns, no matter how disturbing, and chase them wherever they may lead. Whether Nemesis is real or not, its shadow has stretched across decades of research, and in doing so, it's deepened our understanding of extinction, of solar system dynamics, and of our fragile place in the cosmos. Even now, as you listen to this, the Oort Cloud sits in silence. Billions of frozen relics wait in darkness. Maybe they'll never move. Maybe Nemesis is gone. Or maybe, just maybe, it's on its way back. Moving slowly, invisibly, on a 26 million year orbit. A cosmic pendulum. A silent reaper. A myth written in gravity and time. If Nemesis exists, we have to confront another important question. How did it come to be? To understand that, we must journey back to the very beginning of the solar system itself, over 4.6 billion years ago, to the dense molecular cloud that birthed our Sun and its planets. In stellar nurseries across the galaxy, it is common for stars to be born not alone, but as part of pairs, triplets, or even larger stellar groupings. This happens because the gravitational collapse of a massive cloud of gas and dust doesn't always result in a single dense core. Instead, multiple dense regions may form and collapse simultaneously, each one potentially becoming a star. These are the seeds of binary and multiple star systems. In fact, statistical studies suggest that the majority of stars in the Milky Way have at least one stellar companion. This observation led scientists to a bold question. Why would our Sun be an exception? Could we have once had a sibling star that got ejected? Or is it still out there, orbiting distantly and coldly in the darkness? One theory posits that Nemesis formed alongside the Sun but ended up on a wide, elliptical orbit far beyond the Kuiper belt, where dwarf planets like Pluto and Eris reside. Over billions of years, its gravitational influence would be minimal on the inner solar system but significant on the Oort Cloud. This allows Nemesis to remain hidden yet powerful, a galactic sniper with a timetable measured not in years or centuries, but in geological epochs. Another fascinating possibility is that Nemesis isn't bound to us in a perfect, stable orbit. Instead, it may follow a path that is subtly affected by the gravitational tides of the Milky Way itself. As the solar system orbits the galactic center every 225 to 250 million years, it bobs up and down relative to the dense galactic plane. This vertical oscillation could disturb the orbit of a distant companion star like Nemesis, occasionally nudging it closer to the inner solar system and triggering showers of comets. In this scenario, the Sun's galactic environment becomes a participant in the extinction cycle. Nemesis is not acting alone, its rhythm is influenced by our position in the galaxy. It is, in a way, a cosmic metronome set not only by its own orbit but by the deep gravitational tides of a rotating stellar city. And if Nemesis exists, what else could it have influenced? Some astronomers and astrophysicists speculate that it may not be the only unknown body in the outer solar system. The search for Planet 9, a hypothetical massive planet beyond Neptune, was also triggered by the strange orbits of distant trans-Neptunian objects. These objects appear to be clustered in a way that suggests the influence of an unseen massive planet. While Planet 9 and Nemesis are not the same, the fact that both hypotheses arose independently based on gravitational anomalies suggests a broader truth. We do not yet fully understand the architecture of our own solar system. The outer solar system is still a frontier. A vast, uncharted ocean of icy bodies and faint gravitational whispers. While telescopes scan the heavens and infrared surveys probe the dark, much of what lies beyond the Kuiper belt remains a blank slate. It's entirely possible that more than one massive, dim object lurks beyond our vision, not just Nemesis, but others. Brown dwarfs, rogue planets, ancient failed stars. The boundary between what's known and what's imagined is blurrier the further out we go. And so, the mythos of Nemesis continues to evolve, not merely as a possible object, but as a conceptual framework. Even if no such star exists, Nemesis represents our attempt to impose order on chaos. To take the terror of mass extinctions, random, violent, and seemingly senseless, and give them structure, a logic, even a kind of inevitability. It is a psychological salve, a narrative that makes the vast, impersonal cosmos feel just a bit more comprehensible. It tells us that destruction is not without purpose. That history, even catastrophic history, follows a pattern. There is also something distinctly human in the act of myth-making, even in science. The name, Nemesis, was not chosen by accident. In Greek mythology, Nemesis was the goddess of retribution. Her purpose was to enact divine justice, especially upon those who succumbed to arrogance and hubris. In naming this hypothetical star after her, scientists and mythologists alike acknowledge a thematic parallel. Humanity, rising in confidence and power, might one day be brought low not by its own flaws, but by a celestial force it neither sees nor understands. In that way, Nemesis is not just a theory, it is a cautionary tale. It is a reminder that nature does not need to hate us to destroy us. It only needs to be itself. Now, let's venture into an unsettling but fascinating thought experiment. What if Nemesis has already been seen, but not recognized? Consider the possibility that an ultra-dim brown dwarf, so faint it barely registers in the infrared, passed close enough to influence the solar system millions of years ago, but has since drifted beyond our observational range. Its fingerprint would remain not in light, but in the geological and biological layers of Earth's crust. A thin layer of iridium. A sudden die-off. A crater buried under eons of sediment. In such a case, Nemesis becomes not an astronomical object, but a paleontological ghost. Something inferred from broken patterns and extinction curves. We would never see it, only its shadow falling across time. That concept blurs the line between astronomy and deep-time archaeology. It suggests that some of our greatest discoveries might come not from skyward telescopes, but from sediment cores and fossil records. That the key to understanding Nemesis may lie beneath our feet, in the layered record of Earth's memory. And here's where the existential weight of Nemesis deepens. If it does exist, and if it follows a consistent orbit, then we are not just spectators. We are participants in a cosmic countdown. Every orbit brings it closer. Every pass stirs the Oort Cloud. Every disturbance increases the probability of a collision. We are, in that sense, living on borrowed time, not necessarily doomed, but never entirely safe. But there is also empowerment in that realization. Just as Nemesis would be a destroyer, the awareness of such a force could be a motivator. It could drive advances in space observation, planetary defense systems, and our understanding of deep time dynamics. We may not be able to stop Nemesis from stirring comets, but we might one day deflect those comets. We might develop warning systems capable of giving us the years, even decades, needed to prepare. And eventually, we may even gain the capability to leave Earth and colonize other worlds, diversifying the chances of human survival. In that way, Nemesis could be a cosmic catalyst. Not just a bringer of death, but a spur toward evolution, biological, technological, and civilizational. A force that challenges us to grow beyond the Earth, beyond our fragility, into a multi-world species. And isn't that the ultimate irony? That the agent of our extinction might also be the reason we reach for the stars? As of now, Nemesis remains unproven. No telescope has caught it. No gravitational anomaly has demanded its existence. And yet, it lives, in the minds of scientists, storytellers, and seekers of cosmic truth. It is an idea, an echo, a warning. Whether real or imagined, it urges us to keep looking. To question what we think we know. To search the sky not only for beauty, but for danger. And to understand that in a universe this vast, we are always vulnerable, but never powerless. Yet the story of Nemesis remains one of the most haunting examples of how scientific hypotheses and existential fears can intersect in a uniquely human way. It touches on a deep psychological thread that runs through our species, the need to understand, to predict, and to find meaning, even in destruction. Let us now delve even deeper into the scientific efforts that have tried to either confirm or rule out the existence of Nemesis. The first of these came in the form of all-sky surveys, powerful observational campaigns designed to map the entire sky across multiple wavelengths, especially the infrared. These surveys are crucial because a companion star like Nemesis, especially if it is a red dwarf or brown dwarf, would emit very little visible light but could still be detectable in the infrared spectrum. One of the most important of these was the Infrared Astronomical Satellite, IRAS, launched in 1983. It was the first to conduct a survey of the entire sky at infrared wavelengths. When IRAS data was first released, there were tantalizing hints of unidentified objects in the outer solar system. Some speculated these might be distant planets, rogue stars, or possibly even Nemesis itself. However, further analysis revealed that most of these anomalies were either distant galaxies, instrument artifacts, or background noise. Decades later, a far more advanced mission was launched, the Wide Field Infrared Survey Explorer, WISE, which scanned the sky between 2009 and 2011 with unprecedented sensitivity. WISE was capable of detecting objects as cool as 150 Kelvin, far colder than any main-sequence star, at distances up to 10 light-years. If Nemesis were a brown dwarf within that range, WISE would have likely seen it. But WISE found nothing. At least, nothing matching the predictions of a Nemesis-like object. No nearby brown dwarf. No infrared anomaly. This absence of evidence led many in the scientific community to conclude that Nemesis, if it exists at all, must be even further away or even colder and dimmer than expected, possibly a rogue planet or a black dwarf, which emits almost no detectable radiation at all. But black dwarfs, the theoretical end state of white dwarfs, would require more time to form than the current age of the universe allows, so that possibility remains exceedingly unlikely. However, absence of evidence is not evidence of absence. Just because WISE did not find Nemesis does not mean it isn't out there. Our ability to detect extremely faint objects diminishes rapidly with distance. An ultra-cool brown dwarf more than a light-year away might remain undetectable with current technology, blending into the infrared background of the cosmos. It's also possible that Nemesis is in a highly inclined or eccentric orbit that keeps it far out of our observational sweet spots most of the time. Then there's the matter of orbital mechanics. If Nemesis had a highly elliptical orbit around the Sun with a period of, say, 26 million years, enough to line up with the periodicity of mass extinctions, its aphelion could be thousands of astronomical units, AU, away. For context, $1 is the distance from the Earth to the Sun. The Oort Cloud, which marks the extreme edge of our solar system, may extend up to $100,000. Nemesis could lie buried deep in that domain, so distant that even the most advanced telescopes failed to see it. But what if we've been looking in the wrong way altogether? Perhaps the search for Nemesis shouldn't be focused solely on visual or infrared confirmation. Perhaps we need to be looking for patterns, gravitational influences on long-period comets, odd tilts in the orbits of distant Kuiper belt objects, or clustering in the trajectories of outer solar system bodies. This is how Planet 9 was hypothesized, through the unusual clustering of orbits of distant icy bodies that suggested the gravitational pull of a massive, unseen object. Could Nemesis be related to Planet 9? The two ideas are not mutually exclusive. Planet 9 is hypothesized to be a Neptune-sized planet, possibly 10 times the mass of Earth, orbiting at a distance of hundreds of AU. While not a star, its gravitational influence could still account for some of the orbital irregularities seen in the outer solar system. Some researchers even suggest that what we've attributed to Planet 9 could, in fact, be the influence of an even more distant and massive object, possibly Nemesis itself. Alternatively, Planet 9 and Nemesis could coexist, forming a hidden architecture in the solar system's farthest reaches, a place where planetary science meets the unknown. Yet, the Nemesis hypothesis also faces significant criticisms. One major argument is that the fossil record does not show a perfect, uninterrupted pattern of mass extinctions occurring every 26 million years. While some extinction events do appear to line up, others do not. Evolutionary processes are complex, and extinction events can be caused by a wide range of factors: volcanic activity, changes in sea levels, climate shifts, supernovae, and yes, asteroid or comet impacts. Skeptics argue that trying to force these events into a neat periodic cycle risks confirmation bias. The data may be too noisy to support such a rigid periodicity, and attributing the cause to a single celestial body may oversimplify a highly complex and multivariable phenomenon. But supporters of the Nemesis hypothesis counter that even an imperfect pattern might have a root cause, and that such patterns do not need to be exact to reflect a real influence. A slightly perturbed orbit, the gravitational interference of passing stars, or the oscillation of the solar system within the galactic disk could all modulate Nemesis's influence in irregular ways. The extinction pulse doesn't need to strike on a strict timetable. Like a great pendulum swinging through a chaotic system, Nemesis might still be real even if it doesn't operate like clockwork. Another line of defense for the hypothesis is the presence of craters on Earth and the Moon. Impact events leave scars that persist for eons. By dating these craters, scientists can reconstruct a timeline of collisions. Some research has suggested a clustering of impact events, which might align with Nemesis's supposed orbital period. However, crater preservation is also subject to erosion, subduction, and other geological processes, meaning our sample may be incomplete or skewed. So, Nemesis remains in limbo, a concept that exists on the edge of current knowledge, not yet confirmed, not yet refuted. But it's more than a search for a hypothetical star. It's a case study in how science works at the frontier of the unknown. It shows how ideas evolve, from a simple attempt to explain extinction cycles, to a sprawling theory involving orbital dynamics, galactic tides, stellar formation, and observational astronomy. Nemesis challenges us to consider not just the limits of our instruments, but the limits of our imagination. And that may be the most enduring legacy of the Nemesis hypothesis, its power to stretch the human imagination, to make us ask profound questions about time, existence, and the vulnerability of life. To see our solar system not as a self-contained bubble, but as part of a larger galactic ecosystem, influenced by forces that operate over tens or even hundreds of millions of years. In that sense, Nemesis is not just a hypothesis. It is a philosophical mirror. It reflects our fears, our hopes, and our yearning to know what lies in the dark. Because whether Nemesis is real or not, the fact that we imagined it, that we dared to name the darkness, is a testament to the human spirit. And so, we find ourselves poised at the edge of certainty, staring into the cosmic abyss, still wondering if Nemesis, this dark twin, this shadow star, truly exists or is simply a byproduct of our need to find order in chaos. In the grand theater of the cosmos, the search for Nemesis isn't just a hunt for a celestial body, but a journey into the structure of reality itself. To truly grasp the implications of Nemesis, we must revisit the galactic context in which our solar system resides. The Milky Way is not a static environment. It is a turbulent, dynamic ecosystem filled with stellar nurseries, rogue planets, molecular clouds, magnetic fields, and passing stars. Every few million years, the Sun, and by extension, our entire solar system, orbits through different regions of the galaxy. This galactic orbit takes approximately 225 to 250 million years to complete one revolution, known as a galactic year. During this orbit, the solar system passes through the galactic plane, a densely populated region filled with stars, dust, and gravitational perturbations. Some astrophysicists have speculated that these galactic crossings may coincide with mass extinction events on Earth, possibly through mechanisms like increased cometary bombardment or exposure to nearby supernova radiation. The role of Nemesis in this narrative could be that of an intermediary, a gravitational catalyst triggered into action by galactic forces that then disrupts the inner Oort cloud and sends death from above. In this way, Nemesis becomes not only a companion star but a victim of galactic circumstance, a pawn in the far larger cosmic ballet. It's an idea that resonates deeply with human experience, that even the seemingly eternal and stable can be shaped by forces beyond their control. That stars, like civilizations, are vulnerable to their environment. Now consider another possibility. If Nemesis exists, and has a very long, elliptical orbit, then it may have visited the inner solar system many times in Earth's past. Each pass would trigger a different wave of cometary incursions, possibly spread out over thousands of years. This would produce not a single apocalyptic event, but a series of heightened risks over an extended period, a comet storm rather than a singular impact. In such a scenario, Nemesis would not be the hammer that strikes the Earth, but rather the hand that tips the bucket. It would perturb long-dormant icy bodies in the Oort cloud, sending them on chaotic trajectories inward. Some would fall harmlessly into the Sun, others might be ejected from the solar system altogether, and a few, just a few, might strike Earth with devastating consequences. This fits with certain extinction patterns in the fossil record that show prolonged stress and die-offs rather than instantaneous annihilation. These patterns also open the door to another, often overlooked question. If a Nemesis-like body had indeed caused major extinction events, could it have also played a role in seeding life? It's an eerie mirror. If it had the power to destroy, might it also have had the power to create? Consider this: comet impacts, while deadly, also deliver essential building blocks for life. Water, carbon compounds, and even amino acids have been detected in comets. It's conceivable that some of the early ingredients necessary for life on Earth were delivered via these cosmic messengers. If Nemesis played a role in shaking loose these carriers of life's potential, then its influence is paradoxically both life-giving and life-taking, a cosmic gardener wielding both shears and seeds. This duality transforms Nemesis into a truly mythic figure. In Greek mythology, Nemesis was the goddess of retribution, of balance, of cosmic justice. The celestial Nemesis, too, seems to offer balance, an agent of destruction that also plays midwife to new beginnings. If such a body exists, it serves as a grim reminder that in the cosmos, the forces that extinguish can also renew. The same event that wiped out the dinosaurs, after all, cleared the ecological stage for mammals to rise and, eventually, for humans to emerge. But how would we know if Nemesis had passed close to us in the distant past? What evidence might it leave behind? One clue may lie not in the heavens, but buried deep beneath the earth, in the geologic record. Layers of sediment and rock capture the aftermath of cataclysmic events, spikes in iridium levels, shocked quartz, microtectites, and other markers of high-energy impacts. When multiple impact signatures are found in a narrow geologic window, scientists begin to suspect a larger pattern. Some of these windows coincide with extinction events, such as the Chicxulub impact 66 million years ago. But others appear in isolation or in clusters, forming patterns that suggest comet showers rather than isolated asteroid strikes. These patterns, though subtle, might be the ghostly fingerprints of Nemesis, silent testimonies to past visitations. There are also clues in the behavior of distant objects in the solar system. The orbits of long-period comets, the distribution of Kuiper belt objects, and the peculiar tilts of certain dwarf planets may all hint at unseen gravitational influences. These anomalies don't definitively point to Nemesis, but they keep the mystery alive. More speculative still are theories that link periodic cosmic catastrophes to the Sun's motion through the galaxy, particularly through the spiral arms, which are dense regions rich in gas, stars, and potential hazards. If Nemesis were loosely bound to the Sun and more sensitive to galactic tides during these crossings, its disruptive effects could be amplified during these periods. It would become a galactic trigger mechanism, firing comet storms whenever the solar system enters hazardous territory. Interestingly, there are cultural and mythological echoes of Nemesis in ancient stories. Many civilizations speak of dark twins, hidden suns, or destroyers that visit periodically. Of course, these myths cannot be taken as literal scientific evidence. But their psychological resonance, their persistence across time and cultures, may suggest that humanity has long sensed its vulnerability to the unknown. The concept of Nemesis taps into that deep current of cosmic anxiety. And yet, the real allure of Nemesis may lie in its status as a boundary object, something that exists at the limits of science, myth, observation, and imagination. It challenges us to improve our instruments, refine our models, and expand our thinking. It keeps alive the spirit of inquiry, the willingness to ask daring questions even when the answers lie beyond our reach. In the coming decades, new missions may further probe this enigma. The Vera C. Rubin Observatory, for example, will soon begin its deep sky survey, capturing detailed images of the entire southern sky every few nights. Its sensitivity to faint moving objects could help detect distant celestial bodies far beyond the current capabilities of other observatories. Meanwhile, future infrared missions like the James Webb Space Telescope and its successors may provide even greater insight into the cold, dark regions of the cosmos. If Nemesis is out there, dim, cold, and lurking, these instruments may finally catch a glimpse. But even if they don't, the search itself has value. It teaches us about the architecture of the solar system, the nature of orbital dynamics, and the fragility of life on Earth. It reminds us that we are not immune to cosmic forces, that our existence hangs in a precarious balance shaped by things we may not yet see or understand. The story of Nemesis, then, is not just about a hypothetical star. It's about the eternal tension between knowledge and uncertainty, between light and darkness, between the seen and the unseen. And perhaps that's why it continues to fascinate, because in trying to find Nemesis, we are also trying to find our place in a vast, uncaring cosmos. We are seeking order, seeking meaning, seeking the patterns that might help us navigate the unpredictable future. Because hidden in the night sky, among the countless stars and swirling clouds of interstellar dust, there may still be forces we do not yet comprehend, ancient, quiet, and powerful. And whether or not Nemesis exists, the shadows it casts in our minds remind us of how much we have yet to learn. Yet even as we advance technologically and refine our theories, the quest for Nemesis forces us to confront the limits of detection itself. The hypothetical nature of this dark companion stems not only from the absence of direct observation, but also from the incredible difficulty of perceiving something so inherently elusive. If Nemesis were a brown dwarf, or even a very dim red dwarf, its emitted light would be vanishingly faint. It would not glow like our sun or even reflect much light from other stars. Instead, it would radiate primarily in the infrared, blending into the cold background of the universe like a whisper lost in a storm. And this raises a haunting question: how many other celestial bodies are out there, unseen and undetected, wandering the vastness beyond Pluto's orbit? In the outermost reaches of the solar system, the so-called deep freeze, beyond the Kuiper belt, space becomes less of a frontier and more of a blind spot. Our telescopes, magnificent though they are limited by distance, darkness, and angle. A body like Nemesis, moving slowly in a wide arc, could very well escape notice for centuries, unless, of course, it sends something our way. The notion of celestial threats emerging from the dark recesses of the solar system is not without precedent. Consider the discovery of Oumuamua in 2017, an interstellar object passing through our solar system at high speed. Its hyperbolic trajectory and unexplained acceleration puzzled astronomers. Though it wasn't dangerous, it served as a potent reminder that not everything in the sky moves in predictable loops. There are intruders, visitors, and perhaps even sleepers, ancient bodies locked in long, eccentric orbits waiting for the right gravitational nudge. And what if Nemesis isn't alone? What if it's part of a more complex system, a binary companion to the Sun with its own suite of minor planets, rogue moons, or icy debris? Some researchers speculate that Nemesis could be linked to the hypothetical Planet 9, a massive, yet undiscovered planet thought to explain the strange clustering of orbits in the outer solar system. If both Planet 9 and Nemesis exist, could they be remnants of the same early gravitational chaos? Could Nemesis be the parent body that flung Planet 9 into its distant orbit? These ideas, while speculative, are not born of fantasy. They emerge from legitimate anomalies in our data, from celestial mechanics that don't quite add up. Orbital resonances, eccentricities, and unexpected clustering all point toward unseen influences. While no single piece of evidence confirms Nemesis, the accumulation of clues makes it harder to dismiss entirely. The cosmos, after all, is not always forthcoming with its secrets. Sometimes, the truth is written not in the stars we can see, but in the behavior of those we cannot. Beyond the physical search lies a psychological dimension, one that explores how Nemesis, as a concept, captures our collective imagination. It's a shadow that reflects our existential fears, extinction, isolation, the fragility of civilization. It echoes our myths, feeds our stories, and embodies our anxieties. In a universe that is indifferent to our existence, Nemesis becomes the personification of cosmic reckoning. It's important to acknowledge that the scientific community remains divided. Many astrophysicists have moved on from the idea of Nemesis, preferring less dramatic explanations for extinction cycles and orbital anomalies. They point to statistical randomness, terrestrial causes, or other astronomical phenomena as more plausible drivers. But even these skeptics admit the value of the search, not because they believe Nemesis is likely, but because the investigation sharpens our understanding of everything else. Indeed, in pursuing Nemesis, we've deepened our grasp of cometary dynamics, refined models of the Oort Cloud, and improved infrared survey capabilities. The process of ruling out Nemesis has enriched science in ways that its actual discovery might not. And yet, the door remains ajar. Imagine for a moment that Nemesis is real, and that it's still out there, hundreds of billions of kilometers away, slowly making its arc through the cosmos. What would it look like? A dim ember in the void, silent and ancient. Perhaps it once burned brightly, a red dwarf born alongside our sun, but it has since faded into near invisibility. It could harbor its own system of icy bodies, distant echoes of our own solar system's architecture. And every 26 million years or so, as it swings closer, its gravity disrupts the tranquility of the outer solar system, unleashing chaos that takes millennia to play out. We may never witness one of its passes firsthand. Human history is but a blink in galactic time. But the fossil record may hold the story of its past visits, a legacy written not in ink, but in extinction layers and shattered timelines. And in the event that we one day detect such a body, it would be both exhilarating and terrifying. For while the discovery would solve a cosmic mystery, it would also force us to grapple with the implications. Could another wave of extinction be inevitable? How much time would we have to prepare? And would preparation even be possible? These are not idle speculations. The potential for long-period celestial bodies to threaten life on Earth is one of the reasons why planetary defense has become a growing area of focus. Space agencies like NASA and ESA have begun developing impact monitoring systems, asteroid deflection technologies, and international coordination plans. But these efforts are primarily aimed at near-Earth objects, threats we can see and track. Nemesis, if it exists, would challenge that paradigm. It would remind us that not all threats are visible, and not all timelines are human. This tension between the visible and invisible, the known and unknown, lies at the heart of the Nemesis mystery. It is a scientific ghost story, rooted in orbital mechanics, paleontological patterns, and the limitations of our instruments. And like all great mysteries, it inspires not just fear, but wonder. For in the end, what is Nemesis but a reflection of the cosmic scales we rarely think about? The passage of millions of years, the sweeping arcs of stars, the silent interplay of gravity and time. It's a reminder that the universe is not static, that the heavens are not immutable, and that the forces shaping our world may be vast, distant, and invisible. To seek Nemesis is to stand beneath the stars and ask, what else is out there? What sleeps in the dark? What might awaken? And as long as we continue to ask those questions, we remain explorers, not just of space, but of mystery itself. The quest for Nemesis touches more than just science. It taps into something archetypal within us. It's not just about a dark companion star. It's about our human need to understand why things happen, especially on cosmic scales. We seek order in the seeming chaos of extinction events, looking for patterns and purpose in the abyss of time. When we learn that mass extinctions may have occurred on a regular rhythm, our instincts push us to search for a celestial metronome, a hidden partner in the solar system's dance whose slow, majestic orbit casts deadly shadows every 26 million years. But suppose Nemesis is not a star, not a brown dwarf, nor even a visible object in any conventional sense. What if it's something stranger? A massive object composed of dark matter, undetectable by light, but capable of disturbing the orbits of distant comets and asteroids. While this idea stretches into the speculative, it has gained some theoretical interest in cosmology. Dark matter, an invisible form of mass that makes up most of the matter in the universe, has gravitational effects that we observe on galactic scales. If a concentrated clump of it were to drift near the Oort Cloud, it might disturb enough icy bodies to cause a rain of impacts on the inner solar system. Could Nemesis be more than just a faint star? Could it be a shadow made of mass itself? Another wild idea: Nemesis might not be gravitationally bound to the Sun at all. It could be a rogue star or object passing nearby on a long, looping trajectory, periodically disturbing the system and then moving away. Such rogue stars do exist. Many have been detected wandering the galaxy, expelled from their original homes by gravitational interactions or collisions. If one of them were passing close to our solar system every few tens of millions of years, we might misinterpret its visits as part of a bound orbit. It wouldn't be a companion star, but a repeating cosmic intruder. Whatever form Nemesis might take, star, brown dwarf, dark matter mass, or rogue interloper, the challenge remains the same: how do we find it? That's where infrared astronomy becomes essential. Unlike visible light, infrared radiation allows us to see heat. A dim object that emits little to no visible light may still glow in the infrared. Instruments like NASA's Wide Field Infrared Survey Explorer, WISE, were designed to scan the sky in infrared wavelengths and could, theoretically, detect such objects. But even WISE has its limitations, especially when looking for slow-moving, cold objects in the vast outer stretches of our solar system. In 2014, a major analysis of WISE data concluded that there were no Saturn-sized or larger objects within 10,000 astronomical units of the Sun. That puts some constraints on the possible size and distance of Nemesis. But smaller or more distant bodies could still be lurking, perhaps just beyond WISE's ability to detect. That leaves the door open for future missions, like the Vera C. Rubin Observatory, to provide deeper, more precise scans of the outer solar system. With its powerful telescopic reach and its ability to detect subtle movements over time, the Rubin Observatory may finally reveal whether Nemesis, or anything like it, truly exists. Meanwhile, our understanding of extinction events continues to evolve. While asteroid impacts are an obvious and dramatic cause, they are not the only mechanism. Massive volcanic eruptions, climate shifts, and oceanic anoxia, where oxygen levels drop, have all played roles in the history of life on Earth. And here's the crux: some of these processes could themselves be triggered or influenced by extraterrestrial forces. A massive impact could set off volcanic activity or destabilize the climate. So even if Nemesis doesn't directly kill, it may set the stage for death. There is also growing interest in examining isotopic anomalies in sediment layers, chemical signatures left behind during extinction events. For instance, spikes in iridium levels are associated with extraterrestrial impacts, such as the one that likely caused the demise of the dinosaurs. If other extinction boundaries show similar anomalies, and if those anomalies recur at regular intervals, they could serve as a fossilized fingerprint of Nemesis's influence. It's like decoding ancient messages etched into the Earth itself, clues left for us by a universe that does not speak but still communicates. But what if the periodicity isn't real? This is a controversial topic. Some researchers argue that the extinction cycle is a statistical illusion, that when you sift through millions of years of fossil data, patterns are bound to emerge by chance. The 26 million year cycle might be a coincidence, not a cosmic clock. If so, then Nemesis is a solution to a problem that doesn't exist. This scientific debate is a reminder of the dangers of pattern recognition, the human mind's tendency to impose order where there may be none. But even so, the mystery remains unresolved, and the data are tantalizing enough that the question cannot be fully dismissed. It's also worth noting how the Nemesis theory intersects with other ideas about our solar system's structure. The search for Planet 9, a massive, hypothetical planet lurking beyond Neptune, shares some of the same motivations. Astronomers noted that certain objects in the Kuiper belt had unusual, clustered orbits, suggesting gravitational influence from something massive and distant. This rekindled speculation about unseen bodies in the solar system and raised the possibility that multiple undiscovered objects might be shaping the architecture of our cosmic neighborhood. Could Nemesis and Planet 9 be the same object? Possibly, though their expected characteristics differ. Planet 9 is thought to be a super-Earth, perhaps 5 to 10 times the mass of our planet, and lies somewhere between 400 and 800 Australian dollars from the Sun. Nemesis, if it exists, is expected to be farther out and more massive, potentially as much as 0.1 to 0.5 solar masses. But the mere fact that we're considering such questions shows how little we still know about our own backyard. Even our concept of the solar system may be too limited. Traditionally, we consider it to extend out to the Kuiper belt or perhaps the edge of the Oort Cloud. But the Sun's gravitational influence may reach much farther, and its past interactions with neighboring stars in the Milky Way may have shaped the system in ways we don't yet understand. Perhaps Nemesis was once a close companion that drifted away. Or perhaps it was captured, snared by the Sun's gravity during a brush with another star system. Stellar capture is rare, but not impossible, especially in the dense environments where stars are born. And that leads us to consider Nemesis not just as an object, but as a participant in a much larger story, a cosmic ballet of creation, collision, and evolution. In the early solar system, chaos reigned. Planets migrated, moons were exchanged, and gravitational forces hurled bodies into strange new orbits. In such an environment, the emergence or capture of a second star, even a dim one, would not be surprising. It would, in fact, be expected. So what does all this mean for us? Why should we care about a star that may or may not exist, that lurks in the farthest reaches of space? Because the search for Nemesis teaches us humility. It reminds us that even with all our technology, all our knowledge, we are still at the mercy of forces we do not fully comprehend. It reminds us that the Earth is not an island, but part of a vast, dynamic, and often unpredictable system. And more than that, it teaches us wonder. The universe is not dead, but alive with possibilities. Every hypothesis, every theory, every mystery is an invitation to look deeper, to ask more questions, to push the boundaries of what we know. Whether Nemesis is real or not, its story, half science, half legend, is already part of the human journey. It is a mirror we hold up to the sky, asking what might be waiting in the shadows. The search for Nemesis, regardless of its physical reality, reveals something profound about the human condition, our insatiable desire to connect the dots, to build narratives out of the silent movements of the cosmos. This journey is as much philosophical as it is scientific. We gaze into the void not only for knowledge, but also for meaning. Nemesis, in this context, becomes a symbol, an unseen player in a vast story, an echo of celestial influence, and perhaps, a cautionary reminder that we are not in control. As technology continues to evolve, we are entering an era where the boundaries of detection are being pushed further than ever before. Instruments like the James Webb Space Telescope, though not designed to search the outer solar system, are capable of unprecedented infrared observations. And future surveys from the Vera C. Rubin Observatory promise to unveil thousands of faint, slow-moving objects. These tools may not directly find Nemesis, but they will map the region of space where Nemesis would reside, indirectly confirming or ruling out its presence. Meanwhile, other researchers are studying the deep time behavior of comet showers. If we cannot find Nemesis directly, perhaps we can reconstruct its wake, an imprint in the form of periodic increases in long-period comet impacts on Earth. This is where computational astrophysics plays a crucial role. By simulating millions of comet orbits over tens of millions of years, scientists can look for patterns and correlations between solar system dynamics and mass extinction events. If the comet showers can be traced back to a consistent gravitational source in a repeating cycle, that would be compelling circumstantial evidence for something like Nemesis. But what makes this theory so tantalizing is also what makes it elusive. Nemesis, if real, exists on timescales and distances that defy our usual intuitions. Imagine an object that takes 26 million years to complete just one orbit. To us, caught in the brevity of a human lifespan, this is an almost meaningless figure. It's the orbit of deep time, beyond the pulse of civilizations, beyond the rise and fall of species. And yet, its gravitational signature could ripple across epochs, its presence felt in the geological strata long after it has passed silently through the night. This is not just a story about astrophysics. It's about perspective. We live in a tiny window of time, on a fragile rock, orbiting a middling star in an unremarkable part of the galaxy. But when we look for Nemesis, we are reaching across millions of years, trying to make sense of patterns so vast that they almost transcend comprehension. This effort is noble. It connects us to the grand architecture of the cosmos. And even if Nemesis is ultimately disproven, the search for it sharpens our tools, deepens our understanding, and broadens our sense of place in the universe. And yet, the possibility remains that we have simply not looked hard enough. Space is big, so vast, in fact, that even nearby regions of our own solar system remain unexplored. The Oort Cloud, from where Nemesis would exert its influence, is a theoretical construct. No spacecraft has ever visited it. No object has ever been directly observed within it. It is a shell of icy bodies that may stretch from 2,000 to 100,000 astronomical units from the Sun. Within this darkness, the rules change. The density of objects is low, but the gravitational potential is enormous. And it's here, in this near-interstellar void, that Nemesis would reside. Let us consider the nature of such a hypothetical orbit. If Nemesis does exist and orbits the Sun every 26 million years, it must follow a highly elongated elliptical path. At its closest approach, called perihelion, it would interact with the outer Oort cloud, disturbing comets and potentially sending some toward the inner solar system. Then, as it swings out toward aphelion, the farthest point of its orbit, it would retreat into the blackness, essentially invisible to us. It would spend most of its time out there, moving slowly under the sun's distant pull, before returning to shake the cosmic dice once again. Now, to imagine such a body with mass, perhaps 0.1 solar masses, is to consider a gravitational partner of immense force. It would not just influence comet orbits, but potentially perturb other distant objects, altering the dynamics of the solar system's edge. This is why some argue that the orbits of trans-Neptunian objects, such as Sedna and others with extreme, detached orbits, might hint at the gravitational tug of something massive. However, this is also the territory where Planet 9 theories take hold, and the distinction between Nemesis and Planet 9 begins to blur. Could the answer lie in synthesizing these ideas? Perhaps there isn't just one unseen body in the outer solar system, but several. Perhaps Nemesis and Planet 9 are part of a complex, dynamic cluster of distant objects that interact over long timescales, influencing everything from comet paths to extinction events. If so, our current models of the solar system are dramatically incomplete. We may be living in a system that is far more complex, far more chaotic, and far more mysterious than we ever imagined. And it's not just astronomical implications we must consider. The very notion of Nemesis challenges our cultural and psychological assumptions. The name Nemesis was not chosen lightly. In Greek mythology, Nemesis was the goddess of retribution, balance, and justice. Her role was to punish hubris, to bring down those who dared to defy the gods. The idea that nature itself might contain such a mechanism, a hidden partner that brings ruin in a predictable cycle, carries mythic weight. It resonates with ancient fears and archetypes. It's no surprise that the idea of a Death Star orbiting our sun has captured the public imagination. But this metaphor is powerful because it's rooted in a fundamental truth: extinction is part of life on Earth. It is not a rare exception but a recurring theme. Over 99% of all species that have ever lived are now extinct. Mass extinctions have reset the evolutionary clock multiple times, wiping the slate clean and allowing for new forms of life to emerge. If Nemesis plays a role in this process, then it is not just a destroyer, it is also a creator, a silent hand shaping the course of life across eons. Imagine, then, the next extinction event, not one caused by human activity, but one heralded by the slow return of an unseen star. We might detect it only in subtle orbital shifts, or perhaps in a sudden uptick in long-period comet sightings. Eventually, one would be on a collision course. Would we be ready? Would we even understand what we were seeing? Or would Nemesis, once again, strike from the void with no warning, leaving only a scar in the geological record and a mystery for future life to ponder? This scenario is grim, but it's also a call to action. If Nemesis exists, then understanding it becomes a matter of existential importance. It becomes the ultimate case of planetary defense. And if it does not exist, then the mystery of extinction cycles remains unsolved, a tantalizing clue to a deeper truth still waiting in the darkness. The story of Nemesis is not about certainty. It is about possibility. It is about the courage to ask dangerous questions and the humility to accept that we may never find the answers. But even in our uncertainty, there is beauty. Because in looking for Nemesis, we are not just looking for a star, we are looking for ourselves. We are tracing the long arc of history, following the echoes of distant catastrophes, and daring to imagine a cosmos that is alive, complex, and infinitely strange. We left off contemplating the possibility that Nemesis, if it exists, is not merely a harbinger of destruction but a participant in the grand, cyclical rhythm of life and death on Earth. This rhythm, marked by extinction and emergence, is perhaps the most profound evidence that cosmic forces have sculpted our biological history. The idea that a hidden celestial companion might periodically stir the Oort Cloud and rain down cometary fury on our world raises deep questions not just about the structure of the solar system, but about the very nature of our place within it. As we peer further into the scientific landscape surrounding Nemesis, it becomes increasingly clear that this is a hypothesis built upon converging lines of circumstantial evidence. There's the apparent periodicity in mass extinctions, particularly the 26 million-year cycle proposed by Raup and Sepkoski. There's the structure of the Oort Cloud, a vast spherical shell of icy bodies that seems ripe for disruption. There's the occasional spike in long-period comet impacts, and the strange orbits of objects like Sedna that suggest gravitational nudging by something massive and distant. All of this weaves a web of plausibility, though not yet certainty. To complicate matters, our understanding of the outer solar system is still in its infancy. Consider how little we knew even a few decades ago. Pluto was the 9th and final planet, and the space beyond was thought to be relatively empty. Now we know that the Kuiper belt alone contains thousands of icy bodies, and the Oort Cloud may house trillions. The search for trans-Neptunian objects, TNOs, has revealed worlds larger than Pluto, like Eris, and hinted at a chaotic region shaped by unseen forces. It is here, in this dimly lit wilderness, that Nemesis might dwell, moving slowly, interacting subtly, always just beyond reach. One reason Nemesis remains undetected, if it exists, is the nature of the sky itself. Our telescopes scan the heavens, but they do so with limitations. Most surveys are designed to detect bright, fast-moving objects close to Earth. Nemesis, on the other hand, would be faint, slow, and far away. Even a brown dwarf, a failed star that radiates primarily in the infrared, could easily escape visual detection. Only with highly sensitive infrared surveys like the Wide Field Infrared Survey Explorer, WISE, could such an object be glimpsed, and even then, only if it lies in a region of the sky that has been properly scanned. The WISE mission did, in fact, play a major role in tempering enthusiasm for Nemesis. After scanning the entire sky in infrared, WISE detected no brown dwarfs or stars with masses similar to the Sun within 10,000 Australian dollars. This appears to rule out the existence of a companion as massive as previously theorized, at least within a certain distance. However, this doesn't entirely close the door. Smaller, fainter, or more distant objects could still be lurking undetected. And remember, the farther an object is from the Sun, the more sluggish its orbit becomes, and the harder it is to detect through motion alone. Another complication arises from the debate over extinction periodicity itself. Some researchers argue that the 26 million-year cycle is a statistical mirage, an artifact of how extinction data is categorized or interpreted. Others maintain that the pattern is real, even if its cause is unknown. This scientific disagreement underscores the ambiguity at the heart of the Nemesis theory. It is not just a question of whether Nemesis exists, but whether the foundational pattern it was meant to explain even exists in the first place. Still, the gravitational dance of the solar system is full of hidden partners and unexpected motions. Consider the case of Planet 9, a separate hypothesis suggesting that a massive, Neptune-sized planet resides in the outer solar system, influencing the orbits of distant Kuiper belt objects. Though distinct from Nemesis, the Planet 9 theory shares a similar motivation, unseen mass causing visible effects. Some astronomers have even speculated that Nemesis and Planet 9 might be one and the same, though this would require reconciling differences in mass, orbit, and gravitational behavior. So where does this leave us? In many ways, Nemesis remains in a Schrödinger-like state, both real and not real, a ghost on the periphery of science, waiting to be either confirmed or dispelled. But its legacy is undeniable. The Nemesis hypothesis has pushed astronomy to refine its tools, sharpen its theories, and consider the solar system not as a static, clockwork machine, but as a dynamic, evolving system with hidden depths. Let us not forget the psychological impact of such a theory. The idea that mass extinction events, these profound reshufflings of the biological deck, might have a celestial trigger touches something deep within us. It evokes both awe and dread. We imagine ourselves as the inheritors of a planet repeatedly cleansed by cosmic catastrophe. We wonder how many intelligent species might have risen before us, only to be snuffed out by the return of an unseen star. And yet, this fear also fuels a kind of hope. Because if such patterns exist, and if their causes can be understood, then perhaps they can be anticipated. Perhaps one day, with telescopes scanning deep into the blackness, we will see Nemesis returning, not as a surprise, but as a known actor on the cosmic stage. And with that knowledge may come power, the power to prepare, to defend, or at the very least, to witness with understanding rather than terror. In recent years, new technologies have emerged that might one day settle the question. The Vera C. Rubin Observatory, for example, is poised to conduct the most detailed survey of the night sky ever undertaken. It will scan the entire southern sky every few nights, detecting changes and motion across thousands of objects. Though not specifically designed to hunt distant stars, its ability to track faint, slow-moving objects may incidentally shed light on the possibility of a companion like Nemesis. Similarly, advances in computational modeling allow us to simulate the gravitational effects of unseen bodies more accurately than ever before. By running millions of orbital simulations and comparing them with the observed positions of known objects, scientists can narrow down the regions of space where a body like Nemesis might hide, or rule them out entirely. Meanwhile, astrobiologists are also taking an interest. If Nemesis or something like it does periodically disrupt the biosphere, then it has likely had a profound influence on the evolution of life. Some even speculate that extinction events triggered by celestial mechanisms could serve as evolutionary catalysts, sweeping away dominant life forms and allowing new ones to rise. In this view, Nemesis is not just an executioner, but an agent of transformation. There is a haunting poetry in the idea that the stars themselves might be woven into the story of life on Earth. We tend to think of the cosmos as distant and indifferent, a backdrop for our small dramas. But what if it is more than that? What if the slow movements of dark companions, the silent pull of gravity, and the cold architecture of comet clouds are in fact part of the same story that produced us, thinking, questioning beings who now turn their gaze back toward the heavens? This brings us to a final reflection, not scientific, but philosophical. Whether or not Nemesis is real, the search for it represents the best of what science can be, a bold inquiry into the unknown, driven by curiosity, tempered by skepticism, and grounded in evidence. It is a reminder that the greatest mysteries are not always those we can solve easily, but those that require us to look deeper, to question more profoundly, and to remain open to wonder. And so we watch the skies. We refine our instruments. We run our simulations. We debate and we doubt, but we never stop looking. Because somewhere out there, perhaps in the shadow of the Oort Cloud, perhaps beyond, there may be a dark star, an ancient companion, orbiting silently through the eons, waiting to be known. As we continue to unravel the enigmatic threads of Nemesis, it's important to consider how the idea fits into the broader context of cosmic influence on Earth's history. One of the most fascinating aspects of Nemesis is how it intersects with the story of mass extinctions, those pivotal moments in Earth's history when vast swathes of life vanished, sometimes abruptly, sometimes over millennia. The most famous of these, the Cretaceous-Paleogene extinction 66 million years ago, wiped out the dinosaurs and many other species. While this particular event is largely attributed to the Chicxulub impactor, a colossal asteroid or comet, the idea of periodic comet showers caused by a companion star adds another layer of potential explanation for other extinction episodes. When Nemesis was first hypothesized in the 1980s by physicists and astronomers seeking to explain these periodic extinctions, it sparked an intense debate. If a companion star with a highly elliptical orbit lurked in the far reaches of our solar system, then every tens of millions of years, its gravitational tug could send swarms of comets hurtling inward. These cometary bombardments could then cause repeated environmental disasters, atmospheric disturbances, climate shifts, widespread fires, and the ultimate collapse of ecosystems. Yet, the scientific evidence remains ambiguous. The search for Nemesis in the decades since has been like chasing shadows, no direct detection, only indirect hints. The infrared astronomical satellite, IRAS, in the 1980s and later WISE in the 2010s have scanned the sky with increasing sensitivity, finding no clear evidence of a solar companion star. But the possibility remains open for a faint, cold brown dwarf, or a massive planetary body at extreme distances, possibly thousands of times farther from the Sun than Neptune. Moreover, the dynamics of the solar system complicate the picture. The gravitational influence of the giant planets, Jupiter, Saturn, Uranus, and Neptune, plays a dominant role in shaping the trajectories of comets and asteroids. These massive worlds act as cosmic gatekeepers, sometimes deflecting objects away from Earth, sometimes sending them inward. The presence of an additional star or massive object could dramatically alter these dynamics, perhaps creating chaotic zones where comet showers become more frequent. An intriguing development in recent years is the study of distant trans-Neptunian objects, TNOs, with unusual orbits. Some scientists have suggested that the gravitational pull of an unseen massive planet, sometimes called Planet 9, could explain these anomalies. Although Planet 9 differs from Nemesis in several key ways, the two hypotheses share the principle that hidden massive bodies in the outer solar system may be influencing what we see closer in. The continued search for Nemesis also has implications for understanding the broader structure of our galaxy. Our Sun is not isolated but moves through a complex environment filled with stars, gas clouds, and dark matter. It orbits the center of the Milky Way approximately every 225 to 250 million years, crossing galactic arms, encountering varying gravitational fields, and passing near other stars. Some have proposed that encounters with passing stars or molecular clouds during the Sun's galactic journey could also disturb the Oort Cloud and trigger comet showers, independent of a solar companion. This perspective shifts the focus from a single dark star to a dynamic cosmic neighborhood. The timing of extinction events might thus be influenced by multiple overlapping cycles, orbital periods of potential companions, galactic passages, and local gravitational perturbations. Untangling these factors requires sophisticated modeling and comprehensive astronomical data. The stakes of understanding Nemesis are not merely academic. If such a companion star exists, it represents a long-term cosmic hazard, a slow-moving threat that could one day reignite a period of increased impact risk for Earth. While any such event would likely be tens of millions of years in the future, the very concept challenges us to consider the timescales on which cosmic processes operate, vastly longer than human lifespans, yet deeply relevant to the story of life. It also invites reflection on our ability to detect and respond to extraterrestrial threats. Over the last few decades, the Near-Earth Object (NEO) surveys have cataloged thousands of asteroids and comets that could pose risks to our planet, allowing for potential mitigation strategies. Extending this vigilance to the far reaches of the solar system, searching for Nemesis or similar objects, pushes the boundary of planetary defense into the realm of deep space. Astrophysicists and planetary scientists are thus motivated not only by curiosity, but by the imperative to understand every factor that could impact Earth's future. Advances in telescope technology, data analysis, and space missions are gradually enhancing our ability to survey the distant solar system. Missions like the James Webb Space Telescope, with its powerful infrared capabilities, may provide new avenues for detecting faint, cold bodies that have eluded past searches. Furthermore, the Nemesis hypothesis has inspired a broader appreciation of the complexity and interconnectedness of cosmic systems. The idea that a distant star, moving on a slow, elliptical orbit, could influence cometary patterns in biological history highlights the fragile balance that governs planetary environments. It underscores that Earth's story cannot be told in isolation but is embedded in the vast, ever-changing theater of space. Nemesis remains a tantalizing mystery, part science, part speculation, and part cosmic narrative. It embodies the human drive to find patterns, to explain the unexplained, and to face the unknown with rigor and imagination. Whether future discoveries confirm the existence of Nemesis or consign it to the realm of myth, the quest itself enriches our understanding of the cosmos and our place within it. As we continue to explore and observe, we hold on to the hope that someday, perhaps, the dark companion will reveal itself, not as an ominous force, but as a key piece of the celestial puzzle that has shaped life on our blue planet. Beyond the direct search for Nemesis itself, the hypothesis has spurred a cascade of related inquiries that deepen our grasp of the solar system's outer frontier and the subtle influences that may ripple inward over immense timescales. The Oort Cloud, a vast spherical shell of icy bodies surrounding our solar system at distances up to 100,000 astronomical units (AU), is central to this narrative. It is from this distant reservoir that long-period comets are believed to originate, and it is precisely the Oort Cloud that Nemesis's gravity would periodically disturb. The structure and stability of the Oort Cloud remain subjects of ongoing investigation. The Oort Cloud is thought to be a relic of the early solar system, composed of material left over from the formation of planets. These icy bodies, numbering perhaps trillions, orbit at such great distances that the Sun's gravitational grip is tenuous, making them vulnerable to perturbations from passing stars, galactic tides, and potentially a companion star like Nemesis. When disturbed, some of these bodies may be nudged inward, eventually becoming visible comets that sweep close to the Sun. If Nemesis exists, its orbit would likely be highly elliptical, swinging far from the Sun at aphelion, its most distant point, and coming closer at perihelion. This eccentric orbit would take millions of years to complete, matching the proposed periodicity of comet showers and extinction events, about every 26 to 30 million years, as suggested by some statistical analyses of fossil records. However, the debate over the periodicity and the very existence of this extinction cycle is vigorous. Some paleontologists argue that the fossil record does not support a strict regularity in mass extinctions, which undermines the foundation for Nemesis's supposed role. Others point to alternative explanations for extinction events, such as volcanic activity, climate change, and shifting continental plates. The possibility that Nemesis is not a full-fledged star but rather a substellar object like a brown dwarf, or even a massive planet adds another layer of complexity. Brown dwarfs are objects that occupy a liminal space between stars and planets. They are too massive to be planets, but lack enough mass to sustain hydrogen fusion like stars. These objects emit primarily in the infrared, making them difficult to detect with visible light telescopes. The Wide Field Infrared Survey Explorer (WISE) mission, launched in 2009, conducted an all-sky survey in infrared wavelengths, specifically designed to uncover cool, dim objects like brown dwarfs. The mission catalogued many previously unknown brown dwarfs but found no convincing candidate for Nemesis within the expected parameters. This null result led many in the astronomical community to grow skeptical of the Nemesis hypothesis as a stellar companion, though the possibility of a smaller, more distant, or differently oriented object cannot be entirely ruled out. In addition to direct searches, theoretical models have sought to simulate how such a companion would affect the orbits of Oort Cloud objects. These simulations are complex, involving many variables such as the mass of Nemesis, the shape and orientation of its orbit, and the gravitational influences of other stars and the Milky Way itself. Interestingly, these models reveal that a companion star's orbit would need to be finely tuned to avoid destabilizing the inner solar system, or ejecting planets entirely. This fine-tuning raises questions about how Nemesis could have formed and survived for billions of years in a stable orbit without significant detection. Some researchers have proposed alternative mechanisms for periodic comet showers that do not require a companion star. These include the gravitational effects of the galactic tide, the cumulative pull of the Milky Way's mass distribution on the solar system, as it oscillates up and down through the galactic plane. This vertical oscillation occurs roughly every 30 to 35 million years, intriguingly close to the extinction periodicity suggested by some fossil data. The solar system's journey through denser regions of the galaxy, such as spiral arms packed with gas, dust, and young stars, could also disturb the Oort Cloud. During these passages, close encounters with molecular clouds or passing stars could gravitationally perturb distant cometary bodies, sending them on inward trajectories. The subtlety of these gravitational interactions highlights the complexity of celestial mechanics and the challenge of definitively linking astronomical phenomena with terrestrial extinction events. It also emphasizes that Earth is part of a vast cosmic ecosystem, influenced not only by its immediate surroundings but by dynamic processes occurring on galactic scales. Adding to the intrigue, Nemesis has seeped beyond scientific literature into popular culture, inspiring books, documentaries, and speculative fiction. The notion of a hidden dark star lurking on the edge of our solar system taps into deep human fears and fascinations, of unseen dangers, cosmic cycles of destruction, and the fragile nature of life. Yet, despite its allure, Nemesis remains hypothetical. The absence of conclusive evidence forces us to consider the limits of current technology and observation. Our solar system's outermost regions are sparsely explored, and objects hidden in the cosmic dark are inherently difficult to detect. Future advancements in telescope sensitivity, data processing, and perhaps dedicated missions to the outer solar system may one day reveal more. In the meantime, the Nemesis hypothesis serves as a powerful reminder of how much remains unknown about our cosmic neighborhood. It challenges scientists to push the boundaries of observation and theory, to connect dots across disciplines, and to contemplate the interplay between cosmic forces and the story of life on Earth. As we continue this journey of discovery, the search for Nemesis encapsulates the essence of scientific inquiry, the quest to illuminate the unseen, to question the assumed, and to embrace the mystery that fuels our understanding of the universe. Beyond the direct astronomical investigations, Nemesis has also inspired interdisciplinary research that blends astrophysics, geology, biology, and even climatology to build a fuller picture of Earth's deep-time environment and its cosmic triggers. Scientists examine sediment layers, isotope anomalies, and impact craters alongside fossil data, searching for temporal correlations that might hint at external disturbances. One compelling aspect is the study of isotopic signatures such as iridium anomalies, which often mark asteroid impacts in the geological record. The famous iridium layer at the Cretaceous-Paleogene boundary corresponds with the Chicxulub impact and the mass extinction of the dinosaurs. If Nemesis-induced comet showers were responsible for periodic bombardments, similar isotopic layers might be found at regular intervals corresponding to its hypothesized orbit. However, the Earth's geological record is complex and incomplete. Plate tectonics recycle crustal material, erasing or obscuring evidence of older impacts. Moreover, many mass extinctions show signs of multiple causative factors, including volcanic activity, like the Siberian traps at the end Permian extinction, climate shifts, and oceanic anoxia. This multifaceted causation complicates the search for a singular cosmic driver like Nemesis. Nevertheless, the possibility that Nemesis could trigger comet showers aligns intriguingly with the kill mechanism needed to explain sudden, large-scale extinctions. Cometary impacts could initiate atmospheric dust clouds, blocking sunlight and triggering impact winters, acid rain, and global firestorms, cascading into biosphere collapse. These effects resonate with many extinction theories, and thus Nemesis remains a tantalizing, if unconfirmed, piece of the puzzle. As technology advances, new survey telescopes such as the Vera C. Rubin Observatory promise unprecedented views of the dynamic sky. The Rubin Observatory's Legacy Survey of Space and Time, LSST, will image the entire southern sky repeatedly, tracking moving objects, variable stars, and transient phenomena. This may help identify faint, slow-moving bodies in the solar system's outer reaches, perhaps even a Nemesis-like companion or previously unknown distant planets influencing comet trajectories. In addition, space missions like the European Space Agency's Gaia spacecraft are mapping the positions and motions of over 1 billion stars with exquisite precision. This stellar census allows astronomers to reconstruct the solar system's past encounters with nearby stars, potentially identifying historical flybys that could have perturbed the Oort Cloud and induced comet showers independently of a companion star. Moreover, the rise of machine learning and AI in astronomy accelerates the analysis of massive datasets, helping detect subtle patterns and rare objects hidden among billions of data points. Such tools could uncover faint infrared signatures or anomalous gravitational influences consistent with a Nemesis-like body. In the realm of theoretical physics, hypotheses about dark matter and its distribution around the solar system add another dimension. Some speculate whether local dark matter clumps or interactions could influence cometary orbits. Although speculative, these ideas reflect the expanding frontiers of understanding gravity, mass, and cosmic structure beyond visible matter. The Nemesis hypothesis also intersects with philosophical and existential questions about humanity's place in the cosmos. It invites us to consider that Earth's history, including the rise and fall of species, may be shaped by slow-moving cosmic cycles largely indifferent to life's fortunes. This cosmic perspective deepens our appreciation for the fragility and resilience of life, highlighting the delicate balance that allows civilizations like ours to flourish. Furthermore, the search for Nemesis embodies the scientific spirit, driven by curiosity, open to revision, and grounded in empirical evidence. While initial excitement gave way to skepticism after decades of non-detection, the hypothesis has spurred important discoveries about our solar system's structure and the potential hazards lurking in its depths. The broader lesson may be that science is not about certainty but about progressively refining our models of reality. Whether Nemesis is confirmed, revised, or discarded, the quest propels knowledge forward, sharpens technology, and fuels imagination. Looking ahead, humanity's expanding presence in space may eventually provide the tools to explore these outer reaches directly. Space telescopes, probes, and possibly crewed missions to distant solar system regions could transform speculative ideas into concrete discoveries. By mapping the outer solar system in greater detail, we may find new celestial neighbors or confirm the absence of a dark companion. Until then, Nemesis remains a symbol of mystery at the edge of scientific understanding, a reminder that even our seemingly stable solar system may hold hidden dangers and secrets. It challenges us to keep watching the skies with wonder and vigilance, knowing that the story of Earth is written not just in its rocks and oceans but also in the vast, dark reaches of space. This ongoing pursuit exemplifies humanity's unending desire to comprehend the cosmos, bridging disciplines and inspiring generations to look beyond their horizons, ever seeking the truth about our place among the stars. The Nemesis hypothesis stands at the crossroads of astronomy, geology, and biology, weaving a narrative that stretches across millions of years and vast cosmic distances. Its core idea, that a dark companion star orbiting the Sun triggers periodic comet showers and mass extinctions, touches on fundamental questions about the stability of our solar system and the fragility of life on Earth. To fully appreciate the depth of this hypothesis, we must delve into the complexities of celestial mechanics, the challenges of observational astronomy, and the subtleties of Earth's geological and fossil records. The search for Nemesis began in earnest in the 1980s, inspired largely by paleontological studies that suggested a periodicity in Earth's mass extinctions. These studies proposed that roughly every 26 to 30 million years, life on Earth experienced a significant die-off, hinting at a recurring external trigger. The discovery of the Alvarez hypothesis, which linked the Cretaceous-Paleogene extinction to a massive asteroid impact, had already established that celestial events could profoundly affect life, so it was natural to consider whether such impacts might happen cyclically, perhaps influenced by something lurking on the solar system's periphery. Astronomers proposed that Nemesis could be a red or brown dwarf star, a faint and cold stellar object difficult to detect with visible light telescopes. Red dwarfs are small, dim stars that burn hydrogen slowly and live for trillions of years, while brown dwarfs are failed stars that never ignited hydrogen fusion, emitting mostly infrared radiation. Because Nemesis would be so far from the Sun, likely tens of thousands of astronomical units away, its light would be exceedingly faint, making detection challenging with the technology of the 20th century. To seek Nemesis, astronomers used surveys sensitive to infrared light, which penetrates dust clouds and reveals cool objects. The infrared astronomical satellite, IRIS, launched in 1983, scanned the sky for infrared sources, sparking excitement when some objects were found that fit the profile of a cool companion. However, further analysis discounted these candidates. Subsequent infrared missions like WISE, Wide Field Infrared Survey Explorer, provided even deeper and more comprehensive surveys. WISE's results, released in the 2010s, failed to detect any brown dwarf or stellar companion within the expected range, putting stringent limits on the existence of Nemesis as originally proposed. Despite these null results, the hypothesis has evolved rather than disappeared. Some scientists have suggested that if Nemesis exists, it may be more elusive, perhaps a distant, massive planet-like object sometimes termed Planet X, or Planet 9, with an orbit so large and slow that it has only recently begun to be suspected through indirect gravitational effects on trans-Neptunian objects. This alternative idea broadens the search to consider that massive bodies in the solar system's outskirts could perturb cometary orbits, producing periodic bombardments without necessitating a stellar companion. Meanwhile, simulations of the Oort Cloud's dynamics have provided insight into how external forces shape comet trajectories. The Oort Cloud is believed to be a spherical shell extending up to 100,000 Australian dollars from the Sun, home to trillions of icy bodies left over from the Solar System's formation. Because these objects are so distant, the Sun's gravitational influence is weak, making them susceptible to disruption from galactic tides, the gravitational pull exerted by the Milky Way's disk and bulge, and passing stars. These galactic forces are particularly interesting because the Sun itself moves up and down through the galactic plane, crossing it roughly every 30 to 35 million years. This oscillation may periodically increase gravitational disturbances on the Oort Cloud, sending comet swarms into the inner solar system. This timeline aligns intriguingly with the periodicity of some extinction events, providing a potential explanation that does not require Nemesis. Yet, not all scientists agree on the existence or strength of this cycle. The fossil record is complex and incomplete. Mass extinctions vary in magnitude, timing, and causes. Some extinctions correspond closely with known geological or climatic upheavals, such as volcanic eruptions, ocean anoxia, or rapid climate change. While extraterrestrial impacts have undeniably played a role, especially the asteroid impact 66 million years ago, the notion that these events occur regularly remains contentious. Another critical dimension involves understanding the effects of comet impacts on Earth's environment and biosphere. Comets differ from asteroids in composition and velocity. Their icy makeup and higher velocities can generate intense atmospheric effects upon entry. Large impacts inject dust and aerosols into the atmosphere, blocking sunlight and triggering impact winters, which can collapse ecosystems. Acid rain and wildfires may follow, contributing to mass die-offs. These chain reactions underscore why researchers remain interested in the triggers of comet showers, whether from Nemesis or other sources. Adding to the complexity is the nature of the Oort Cloud itself. Its structure is difficult to observe directly. Our knowledge is largely inferential, based on comet orbits and computer models. Some models suggest the Oort Cloud formed from material scattered outward by the giant planets during the Solar System's early formation, while others propose that it may include captured objects from nearby stars. This last idea hints that the Solar System's environment is not isolated but dynamically interacts with neighboring stars and galactic structures. The hypothetical orbit of Nemesis would be highly elliptical and inclined relative to the ecliptic plane, with an orbital period of tens of millions of years. Over such vast periods, gravitational perturbations from passing stars, galactic tides, and molecular clouds could alter its orbit, possibly causing variations in its influence on the Oort Cloud. This instability could explain inconsistencies in the periodicity of extinctions or impact events, should Nemesis exist. If Nemesis were a brown dwarf, it might emit weak radio signals or have detectable gravitational effects on nearby objects. Efforts have been made to search for subtle perturbations in the orbits of known solar system bodies that could betray an unseen massive companion. So far, no such evidence has been definitive. The discovery of exoplanets orbiting other stars has sharpened methods for detecting faint companions, including astrometry, radial velocity, and direct imaging. Applying these methods to our solar system's outskirts remains challenging but is becoming increasingly feasible. Another fascinating aspect is the potential link between Nemesis and the hypothetical Nemesis comet showers. If Nemesis's gravity nudges Oort Cloud objects inward periodically, this could explain clusters of long-period comet arrivals observed in the inner solar system. The frequency and magnitude of such showers would depend on Nemesis's mass, orbit, and distance, as well as the density and distribution of Oort Cloud objects. Some studies of impact craters on Earth and the Moon suggest that impacts are not randomly distributed in time but show clustering, possibly reflecting comet showers. The Moon's surface preserves an impact record less disturbed by geological processes, making it a valuable archive for studying bombardment history. Understanding whether these clusters correlate with Nemesis's hypothesized cycle remains an ongoing challenge. Beyond scientific inquiry, the Nemesis hypothesis raises profound questions about the nature of life and extinction. If a hidden celestial companion periodically disrupts Earth's biosphere, it implies that life's evolution is intertwined with cosmic rhythms beyond our control. This perspective shifts the narrative from purely earth-bound causes of extinction to a universal interplay between life and the cosmos. In cultural and philosophical terms, Nemesis symbolizes the unknown forces that shape existence, forces that lurk beyond perception but wield immense power. This motif resonates in myths and stories about celestial omens, cycles of destruction and rebirth, and humanity's vulnerability to the vastness of space. As we advance technologically, future observatories, space probes, and computational models will continue to probe the outer solar system's mysteries. Missions like the upcoming James Webb Space Telescope, although primarily designed for distant cosmic observation, may contribute indirectly by improving our understanding of brown dwarfs and planetary mass objects. Dedicated surveys targeting the solar system's periphery may eventually resolve whether Nemesis is real or merely a compelling theory. The interplay between Nemesis and galactic environment also draws attention to the broader cosmic context of our solar system. The Milky Way is not a static backdrop but a dynamic environment where stars move, spiral arms rotate, and dark matter shapes gravitational potential. These factors influence the solar system's stability and could modulate the flux of cometary bodies reaching the inner solar system. Moreover, as humanity contemplates long-term survival and space colonization, understanding these cosmic hazards gains practical urgency. Identifying potential impact risks and their triggers informs planetary defense strategies, guiding efforts to detect and mitigate threats from near-Earth objects. In essence, Nemesis represents a nexus where observational astronomy, theoretical modeling, earth sciences, and existential inquiry converge. It encapsulates humanity's drive to comprehend not just our immediate surroundings, but the hidden forces sculpting the tapestry of life over geological epochs. Ultimately, whether Nemesis is confirmed or remains a tantalizing hypothesis, its legacy endures. It reminds us of the delicate balance between stability and chaos, of the profound links between Earth and the cosmos, and of the endless quest to uncover the secrets veiled in the darkness beyond our sun. The ongoing investigation into Nemesis also invites us to examine the boundaries of scientific knowledge and the ways hypotheses evolve with new evidence and technology. In the early days, the idea of a companion star lurking in the solar system's dark outskirts was speculative but grounded in observable patterns and plausible mechanisms. As instruments improved, the lack of direct detection challenged the hypothesis, yet it remained resilient due to its explanatory power regarding periodic extinctions and comet influxes. This dialectic between theory and observation exemplifies the dynamic nature of scientific progress. One of the fascinating aspects of Nemesis is how it exemplifies the delicate interplay between celestial mechanics and biological consequences. The solar system is not an isolated, static arrangement. It exists within the dynamic environment of our galaxy, subject to gravitational influences and encounters that can ripple across eons. The hypothesized Nemesis star, by perturbing the Oort Cloud, could act as a cosmic trigger, instigating comet showers that bombard Earth with devastating impacts. These impacts can cause climate upheavals, mass extinctions, and evolutionary bottlenecks, thus influencing the trajectory of life itself. The complexity of detecting Nemesis is intensified by the vast distances and faintness involved. At tens of thousands of astronomical units, a companion star would be incredibly faint, emitting primarily in the infrared spectrum, if at all. Brown dwarfs and other substellar objects have temperatures ranging from a few hundred to a few thousand Kelvin, far cooler than our Sun's surface temperature of around 5,800 K. This coolness results in minimal visible light output, making detection challenging without sensitive infrared telescopes. Even with WISE and similar surveys, the vastness of space and background noise complicate efforts. Moreover, the orbital period proposed for Nemesis, on the order of 26 million years, means it would be traveling extremely slowly in its orbit, moving only a tiny fraction of its path within a human lifetime. This slow movement complicates efforts to detect changes in position or gravitational influence. It's akin to trying to observe a distant ship barely moving on the horizon, obscured by fog and darkness. The Oort Cloud itself remains enigmatic, an unseen frontier. Direct observation is currently impossible because its objects are small, dark, and distant. Our knowledge comes from studying the trajectories of long-period comets that enter the inner solar system. These comets' orbits suggest a spherical reservoir of icy bodies extending far beyond Neptune's orbit. The distribution, density, and total mass of the Oort Cloud are still subjects of active research, as is the nature of its interaction with passing stars, the galactic tide, and hypothetical companions like Nemesis. Scientific models simulate how external perturbations can send Oort Cloud objects plummeting toward the Sun. Galactic tides, produced by the gravitational field of the Milky Way, exert a slow but persistent force that can destabilize comet orbits. Passing stars or molecular clouds can induce sudden gravitational shocks, dislodging comets en masse. If Nemesis exists, it would act as one such perturber, periodically sweeping through its elliptical orbit and triggering bursts of comet activity. These comet showers are hypothesized to coincide with spikes in impact craters on Earth and the Moon. The Moon's ancient, relatively unaltered surface provides a historical record of impacts. Studies of lunar cratering patterns sometimes reveal clustering in time, suggesting episodes of intense bombardment. Determining the periodicity and cause of these episodes helps constrain models of solar system dynamics and potential triggers like Nemesis. In the realm of Earth's history, mass extinctions are multifaceted events. The fossil record shows 5 major extinctions, such as the Permian-Triassic and the Cretaceous-Paleogene, that reshaped biodiversity. While asteroid impacts have been implicated in some extinctions, volcanic activity, climate shifts, sea level changes, and other terrestrial factors also play crucial roles. The idea that extraterrestrial influences like Nemesis could add a periodic rhythm to these cataclysms is both compelling and controversial. If Nemesis were confirmed, its discovery would revolutionize our understanding of the solar system's architecture and our place within it. It would represent a hidden actor, silently influencing the fate of Earth over millions of years. This realization would elevate the study of celestial mechanics from abstract astronomy to a direct exploration of factors shaping the history of life. The search for Nemesis also exemplifies the challenges of working at the frontier of detection limits. The faint signals of brown dwarfs or planetary mass objects require not only advanced instruments, but sophisticated data analysis techniques to distinguish them from background stars and galaxies. Infrared astronomy has blossomed in recent decades, with missions like Spitzer, WISE, and ground-based telescopes equipped with adaptive optics, pushing detection capabilities. Yet, the vast sky and the subtlety of signals mean that even today, we may miss faint, distant companions. In parallel, advances in computational astrophysics allow simulations of solar system and galactic dynamics with increasing fidelity. These models can test whether a hypothetical Nemesis's gravitational influence would produce observable effects consistent with known comet influx patterns and extinction timelines. Discrepancies between model predictions and observed data help refine or refute the hypothesis. An intriguing dimension to the Nemesis question is its implication for exoplanetary systems. Many stars have been found to possess multiple companions, including stellar binaries and complex planetary systems. If our Sun harbors a distant companion, it would align with the broader diversity seen in the galaxy. Understanding such systems helps contextualize our solar system's uniqueness or typicality. From a philosophical standpoint, the Nemesis hypothesis challenges the notion of a stable, safe solar environment. It implies that cosmic events beyond human control periodically reshape life on Earth, emphasizing vulnerability and the interconnectedness of cosmic and biological histories. This awareness inspires both humility and curiosity, motivating continued exploration of the dark, distant reaches of our celestial neighborhood. Considering future prospects, the upcoming generation of observatories promises new opportunities. The Vera C. Rubin Observatory, with its wide-field sky surveys, will track transient events and faint moving objects. Its data may reveal unknown companions or transient comet showers. The James Webb Space Telescope, Though focused on distant galaxies and exoplanets, advances infrared detection technology is critical to identifying cold objects. Additionally, proposed space missions aimed at exploring the outer solar system, such as missions to the Kuiper Belt and beyond, may provide indirect clues about distant companions. Gravitational studies of known trans-Neptunian objects can reveal subtle perturbations indicative of unseen massive bodies, potentially related to Nemesis or Planet 9 hypotheses. Public fascination with Nemesis persists because it embodies a cosmic mystery with direct relevance to humanity's survival and evolution. It conjures visions of hidden dark stars, cometary storms, and cyclical destruction, elements of a grand narrative connecting Earth to the farthest reaches of space and time. In the scientific community, Nemesis remains a hypothesis to be tested, refined, or discarded as evidence accumulates. It stands as a testament to the interplay between curiosity, skepticism, and the relentless quest to understand the universe. Whether Nemesis is a shadowy star or a symbol of scientific imagination, it continues to inspire inquiry at the edge of knowledge. As we expand our technological reach and deepen our understanding of galactic dynamics, the question of Nemesis will persist. Will future generations identify a hidden stellar companion shaping Earth's destiny? Or will they find that cosmic rhythms arise from the galaxy's gravitational dance alone, without a Nemesis star? The answers await in the cold, dark expanse beyond Neptune, where mystery endures. Until then, the tale of Nemesis reminds us that the universe is vast, complex, and often stranger than fiction. It invites us to look upward and outward, to question what lies unseen, and to contemplate the forces that have shaped life's fragile existence on this pale blue dot. The concept of Nemesis also encourages us to reconsider the nature of extinction itself, not as isolated catastrophes but as potentially interconnected phenomena influenced by external cosmic cycles. If Nemesis or a similar dark companion star exists, it suggests Earth's history is intertwined with celestial events on scales far beyond human lifetimes. This cyclical perspective brings a broader temporal context to mass extinctions, linking geological and biological records with astrophysical processes, a synthesis that demands interdisciplinary collaboration across paleontology, astronomy, and geology. Examining the timeline of mass extinctions and their possible periodicity reveals a tantalizing pattern. The approximately 26 million year interval corresponds intriguingly with some clusters of extinctions and large impact craters, yet these correlations remain debated. Some scientists propose that this regularity might be an artifact of incomplete data or natural variations rather than a signature of Nemesis. Others suggest that the apparent periodicity could be the result of multiple interacting causes, including galactic plane crossings, molecular cloud passages, and solar system dynamics, with Nemesis being one among several influencing factors. Beyond the immediate impact risk, a dark companion star could exert more subtle influences on the solar system's stability. Over millions of years, its gravity might perturb the orbits of distant icy bodies, sending not just comets but also asteroids inward, potentially increasing the flux of hazardous objects. It could also influence the heliosphere's shape and size, the protective bubble formed by the solar wind, modulating cosmic ray penetration to the inner solar system, with possible implications for Earth's atmosphere and climate. While brown dwarfs are common in the galaxy, the challenge is whether such an object could remain undetected so close to the Sun. Theories propose that Nemesis would be either a faint red dwarf, brown dwarf, or even a massive planet-like object. Each candidate poses different observational challenges and has different predicted effects on the Oort Cloud and comet flux. A red dwarf would be more luminous and easier to detect than a brown dwarf, while a massive planet might be elusive yet still gravitationally significant. Some studies focus on indirect evidence, looking for gravitational perturbations on known trans-Neptunian objects or peculiar clustering of comet orbits that might hint at a distant massive body. These methods are complex because many factors influence orbital dynamics, including Neptune's gravity and collective gravitational effects of small bodies. Separating Nemesis's potential influence from these confounding factors is a major challenge requiring large datasets and precise measurements. The idea of a dark companion star has also permeated popular culture and speculative science, sometimes inspiring apocalyptic narratives or theories about cyclical extinction. While the scientific community remains cautious, such narratives underscore humanity's fascination with cosmic mysteries and the potential fragility of life amid vast, indifferent forces. This fascination fuels public interest and support for astronomy, encouraging investment in observational programs and technology development. Technological advances promise to expand the search space dramatically. The European Space Agency's Gaia mission, which precisely measures the positions and motions of over 1 billion stars, provides invaluable data for identifying nearby objects with unusual trajectories. Gaia's ability to detect subtle gravitational wobbles in star positions may reveal unseen companions or rogue stars, possibly shedding light on the Nemesis question. As we consider Nemesis, it is also essential to reflect on the limits of human perception and the biases inherent in interpreting sparse data over immense timescales. The vastness of space and the faintness of distant objects push our instruments and analytical methods to the edge. Interpreting periodic patterns in extinction and impact events is complicated by incomplete fossil records and dating uncertainties. These challenges remind us that hypotheses like Nemesis are provisional frameworks, evolving as new evidence emerges. Meanwhile, the search for Nemesis has inspired complementary investigations into other possible solar system companions. The concept of Planet 9, a hypothetical massive planet far beyond Neptune, has gained traction due to clustering in trans-Neptunian objects' orbits. Though distinct from Nemesis, Planet 9 shares the theme of hidden influences shaping solar system dynamics. The discovery of Planet 9 or other distant massive objects would deepen our understanding of the solar system's architecture and formation history. In the broader galactic context, the Sun's journey through the Milky Way exposes it to a dynamic environment. Periodic crossings of the galactic plane may increase exposure to dense star fields and molecular clouds, enhancing the probability of stellar encounters and gravitational disturbances. Nemesis, if real, would be part of this grand cosmic interplay, a local actor within the larger galactic drama influencing Earth's fate over geological timescales. Considering cosmic extinction mechanisms also invites philosophical reflections on contingency and resilience. Life on Earth has persisted through repeated crises, adapting and evolving in response to environmental upheavals. The notion of a hidden celestial companion periodically threatening life highlights the precarious balance between stability and chaos in the cosmos. It frames humanity's existence within a narrative of survival amid unpredictable cosmic forces. Further investigations into the Oort Cloud and comet dynamics may clarify Nemesis's role, if any. Space missions targeting comets and Kuiper belt objects yield insights into these distant reservoirs, revealing their composition, structure, and interaction with solar and galactic forces. Understanding these bodies' behaviors helps refine models of comet showers and potential triggers. In parallel, simulations of stellar encounters in the solar neighborhood assess the likelihood of past or future perturbations by passing stars. Such encounters can produce comet influxes independent of a bound companion star, complicating the attribution of observed periodicity solely to Nemesis. The solar system's motion relative to nearby stars and the galactic tide creates a complex gravitational environment shaping the influx of celestial objects. The idea of Nemesis also intersects with the search for life beyond Earth. If extinction events on Earth are influenced by such cosmic cycles, then life's emergence and persistence elsewhere may similarly be affected by local stellar environments and companion stars. This consideration shapes astrobiological models of habitability and the stability of planetary systems. Ultimately, the Nemesis hypothesis embodies the spirit of inquiry that drives astronomy, pushing boundaries, questioning assumptions, and seeking explanations for observed phenomena. Whether Nemesis is confirmed, modified, or abandoned, its legacy persists in advancing our understanding of the solar system and the cosmic forces shaping Earth's history. This continuing quest embodies humanity's drive to understand its origins and fate, blending astrophysics, geology, biology, and philosophy. It invites us to contemplate not only distant stars and icy comets, but also our own place in a vast, ever-changing universe where unseen companions might lurk in the dark, silently influencing the fate of worlds. As we delve deeper into the Nemesis hypothesis, it becomes clear that the quest to detect such a dark companion star pushes the limits of observational astronomy. Current infrared and sky surveys, such as the Wide Field Infrared Survey Explorer (WISE), have scoured the sky for faint, cold objects that might fit the profile of a brown dwarf or massive planet lurking on the solar system's outskirts. WISE's comprehensive infrared mapping, which can reveal objects too cold and faint to be seen in visible light, has yet to identify any compelling candidate for Nemesis. This absence of direct evidence places stringent constraints on the size, luminosity, and orbit of any hypothetical companion, suggesting that if Nemesis exists, it must be exceptionally elusive. The sensitivity of infrared telescopes depends on the object's temperature and distance. Brown dwarfs, often called failed stars, do not sustain hydrogen fusion like regular stars but can emit faint heat signatures detectable in infrared wavelengths. Despite this, a Nemesis-sized object on a wide, eccentric orbit would be cold and dim, potentially slipping below current detection thresholds. Yet, with ongoing improvements in detection technology, including next-generation infrared observatories and ground-based adaptive optics, the window to discover such objects is rapidly expanding. Intriguingly, the notion of a binary or multiple star system involving the Sun is not without precedent. Binary stars are common in the galaxy. Roughly half of Sun-like stars exist in binary or multiple systems. However, the Sun appears to be a solitary star, with no confirmed stellar companion in close proximity. Nemesis would represent an outlier, a very distant, dim companion influencing the solar system subtly over millions of years rather than a close, gravitationally bound twin star. This would raise profound questions about the formation and evolution of our solar system. How did such a companion come to be? Did it form together with the Sun, or was it captured later from the galactic environment? Theoretical models suggest that Nemesis could have originated from the same molecular cloud as the Sun but was ejected into a distant, highly elliptical orbit due to early gravitational interactions. Alternatively, it might have been captured as the solar system traversed the galaxy, ensnared by the Sun's gravity during a close encounter with another star. Both scenarios require precise conditions, making Nemesis an unusual but not impossible feature. Astrophysicists also consider the impact of Nemesis on the solar system's stability. While Nemesis's gravitational influence might be weak at perihelion, its periodic approach could disrupt the distant comet reservoirs, triggering showers of comets into the inner solar system. This influx could heighten the risk of impact events on Earth and other planets, correlating with geological evidence of past extinctions. The timing and scale of these perturbations would depend on Nemesis's orbital parameters, including its eccentricity, inclination, and period. Some researchers propose that Nemesis's orbit could be highly inclined relative to the ecliptic plane, which complicates detection and also affects how it influences comet trajectories. A high inclination orbit means Nemesis might spend most of its time far from the plane in which planets orbit, only crossing closer at specific intervals. Such an orbit could explain the periodicity in comet showers without necessarily causing detectable changes in planetary orbits. The interplay between Nemesis and the Oort Cloud, the vast, spherical shell of icy bodies surrounding the solar system, remains a crucial focus. The Oort Cloud's sheer size, extending up to 100,000 astronomical units (AU) from the Sun, means that even a distant companion could exert significant gravitational forces on its constituents. Comets nudged from stable orbits could be sent plunging towards the Sun, potentially crossing Earth's path. The temporal clustering of such comet showers could then align with periodic extinction events, providing circumstantial support for Nemesis. However, alternative explanations challenge the Nemesis model. Some scientists argue that the galactic tide, the gravitational pull exerted by the Milky Way's disk and bulge, could also cause periodic disturbances in the Oort Cloud. As the solar system oscillates up and down through the galactic plane approximately every 30 million years, this tidal effect might trigger comet influxes independent of any companion star. Distinguishing between Nemesis-induced and galactic tide-induced comet showers is a subtle and complex task requiring extensive data analysis. Moreover, close stellar flybys, nearby stars passing relatively close to the solar system, can also perturb comet orbits. The record of past flybys is reconstructed through careful tracking of stars' trajectories using astrometric data. While these flybys occur irregularly rather than periodically, their potential to induce comet showers complicates the picture further, adding layers of stochastic influences to the relatively neat Nemesis hypothesis. Despite these uncertainties, the search for Nemesis exemplifies the scientific method in action, forming hypotheses based on observed patterns, testing predictions through observation, and revising models in light of new data. This iterative process advances our understanding, even when definitive answers remain elusive. Beyond the scientific realm, Nemesis captivates the human imagination, inspiring narratives that blend cosmic mystery with existential drama. The idea of a dark, unseen star periodically threatening life on Earth evokes themes of fate, vulnerability, and the interplay between chaos and order in the cosmos. Such stories resonate deeply, reminding us of our smallness amid vast, powerful forces and motivating continued exploration. The Nemesis hypothesis also intersects with contemporary discussions on planetary defense and the long-term survival of humanity. Understanding potential cosmic threats is crucial for developing mitigation strategies, whether through improved monitoring of near-Earth objects, space missions to study and potentially divert hazardous comets or asteroids, or advanced warning systems. If a dark companion star contributes to periodic comet showers, recognizing its presence and orbit could be vital for predicting future impact risks. As technology evolves, so do our tools for cosmic exploration. Upcoming observatories, such as the James Webb Space Telescope and next-generation ground-based telescopes like the Extremely Large Telescope, ELT, will enhance our ability to detect faint objects at great distances. These instruments could finally reveal or rule out Nemesis-like objects, shedding light on the solar system's hidden architecture. Meanwhile, advances in computational astrophysics allow scientists to simulate the solar system's evolution under various scenarios, incorporating potential companion stars, galactic tides, and stellar flybys. These simulations provide insights into the dynamic processes shaping comet flux and impact events over geological timescales. The quest for Nemesis ultimately reflects a broader theme in science: the drive to uncover hidden forces shaping our world. Whether it's dark matter in the universe, unseen exoplanets orbiting distant stars, or a dark companion star lurking in our solar system's outskirts, humanity continually seeks to illuminate the unseen. In the context of cosmic mysteries, Nemesis stands as a testament to the complexity and grandeur of the universe. It challenges us to look beyond the familiar, question assumptions, and embrace uncertainty as a pathway to deeper knowledge. While the existence of Nemesis remains unproven, the hypothesis has profoundly influenced our understanding of the solar system's dynamics and the potential links between astronomical phenomena and life on Earth. It continues to inspire research, debate, and wonder, embodying the spirit of exploration that defines humanity's relationship with the cosmos. Exploring further into the implications of Nemesis, one must consider the subtle yet profound influence such a companion star would have had on the evolutionary trajectory of life on Earth. If Nemesis does exist and periodically disturbs the Oort Cloud, triggering comet showers, this could have been a hidden driver behind some of the most dramatic extinction events in Earth's history. The fossil record reveals several mass extinction events that have reset the evolutionary clock, including the well-known Permian-Triassic extinction approximately 252 million years ago, which wiped out an estimated 90% of species, and the Cretaceous-Paleogene extinction around 66 million years ago, famously linked to the demise of the dinosaurs. Scientists speculate whether Nemesis-induced comet showers could explain a cyclic pattern of extinctions observed in some geological records. The theory proposes that every 26 to 30 million years, the gravitational nudging of distant icy bodies by Nemesis sends a barrage of comets into the inner solar system, increasing the odds of catastrophic impacts. These impacts would not only cause immediate destruction but could also trigger long-term environmental changes, blocking sunlight, altering climates, and collapsing ecosystems. If such a periodic trigger exists, it would represent an extraordinary cosmic connection between distant astrophysical events and the biological history of Earth. It would suggest that our planet's evolutionary narrative is not solely shaped by terrestrial forces but is also deeply intertwined with celestial mechanics on a grand scale. This possibility adds a layer of complexity to our understanding of life's resilience and vulnerability, inviting a multidisciplinary approach that spans paleontology, geology, astronomy, and astrophysics. Nevertheless, the Nemesis hypothesis is not without controversy. Critics argue that the statistical evidence for periodic extinction events is not robust enough to conclusively support the theory. Some studies suggest that the apparent periodicity could be a result of sampling biases or incomplete fossil records. Furthermore, alternative explanations, such as volcanic activity, climate change, and sea level fluctuations, offer more immediate and terrestrial causes for many extinction events. From an astronomical standpoint, the absence of direct observational evidence for Nemesis poses a significant challenge. The sky surveys conducted by WISE and other instruments have not found any suitable candidate object in the expected parameters. This null result leads many astronomers to consider that if Nemesis exists, it must be either smaller than expected, extremely faint, or on an orbit even more distant and elongated than initially proposed. It may also be that Nemesis is a rogue object passing through the solar system temporarily rather than a gravitationally bound companion. The search for Nemesis also raises broader questions about the formation and architecture of the solar system. The Sun's environment during its birth was likely a dense star cluster where gravitational interactions were frequent and chaotic. In such a context, the capture of a companion star or a massive brown dwarf would be possible but unusual. This contrasts with the relative stability and isolation the Sun appears to have maintained for billions of years. Interestingly, the concept of a companion star to the Sun extends beyond Nemesis. Another proposed hypothetical companion, dubbed Taichi, was suggested to explain other anomalies in the outer solar system's dynamics, specifically in the distribution of long-period comets. Like Nemesis, Taichi is theorized to be a large, gas giant or brown dwarf orbiting far beyond Pluto, but on a much wider orbit, which would make it even harder to detect. Although data from WISE has largely disfavored Taichi's existence, the possibility of unknown massive objects in the outer solar system remains a tantalizing mystery. The idea of undiscovered large bodies beyond Neptune has recently gained renewed interest with the hypothesis of Planet 9, a potential super-Earth-sized planet influencing the orbits of distant Kuiper belt objects. While Planet 9 is much smaller and closer than Nemesis, its possible existence illustrates how our picture of the solar system is still incomplete, especially in the distant fringes. Nemesis fits into this broader context as a symbol of the hidden complexity lurking in the dark expanses beyond the familiar planetary neighborhood. It challenges astronomers to push the boundaries of observational technology and theoretical modeling to uncover what may be hiding in the shadows. On a philosophical level, the Nemesis hypothesis touches upon profound questions about fate and randomness in the cosmos. If a distant, unseen companion star periodically causes mass extinctions, does that imply a deterministic pattern to life's upheavals? Or is it merely one of many random, chaotic influences in a vast, dynamic universe? This interplay between order and chaos resonates deeply with human curiosity about our place in the cosmos. Furthermore, Nemesis has inspired countless stories in science fiction and popular culture, where it often appears as an ominous harbinger of doom, lurking unseen in the darkness. These narratives reflect our collective fascination with cosmic threats and the fragile nature of life. They also serve as cautionary tales, reminding us of the need for vigilance and preparedness against potential existential dangers. In scientific terms, the investigation of Nemesis has spurred advancements in various fields, from improving infrared survey techniques to enhancing our understanding of comet dynamics. It highlights the importance of interdisciplinary research, combining observational astronomy, celestial mechanics, geology, and biology to tackle complex questions about the past and future of Earth and the solar system. Looking ahead, the ongoing development of powerful telescopes and space missions promises to refine our knowledge of the solar system's outer reaches. missions like the Vera C. Rubin Observatory are poised to dramatically increase the discovery rate of distant small bodies, providing new data that could either support or refute the existence of Nemesis or similar objects. Additionally, improvements in data analysis, including machine learning and artificial intelligence, offer new tools to detect subtle patterns and signals within vast astronomical datasets. These techniques might uncover faint hints of elusive companions or reveal more about the complex gravitational interplays shaping comet populations. The search for Nemesis also aligns with broader efforts to understand near-Earth objects and planetary defense. While Nemesis itself may be far away and difficult to detect, the comets and asteroids it might send inward represent real and immediate threats. Enhancing our capacity to detect, track, and potentially mitigate these threats remains a high priority for space agencies worldwide. In this light, Nemesis embodies the intersection of cosmic mystery, scientific inquiry, and practical concern. It is a reminder that our survival is linked not only to human ingenuity, but also to forces operating on immense scales and deep time frames. Moreover, the concept of a dark companion star challenges our perception of the solar system as a well-charted domain. It invites humility and wonder, suggesting that much remains to be discovered in the cosmic backyard. The ongoing debate about Nemesis exemplifies the dynamic nature of science, how hypotheses evolve, adapt, or fall away based on new evidence, and how unanswered questions continue to fuel exploration. In essence, Nemesis is more than just a theoretical star. It is a symbol of the unknown, a cosmic enigma that beckons us to explore, question, and understand the universe beyond what we currently see. The potential existence of Nemesis opens a window into a universe teeming with hidden dynamics, where even the seemingly stable solar system may harbor surprises with profound implications. If Nemesis is indeed a dim, cold companion star on a distant, eccentric orbit, it challenges our understanding of stellar formation and binary star systems. While binary systems are common in the galaxy, more than half of all stars are estimated to have one or more stellar companions. The Sun is generally considered a solitary star. Discovering a companion star would therefore reshape this fundamental assumption, compelling astronomers to re-examine solar system evolution in the context of binary star dynamics. Exploring how Nemesis might have come to reside in the solar system's outskirts leads us into the realm of star cluster dynamics. When the Sun was born roughly 4.6 billion years ago, it likely formed in a dense stellar nursery with dozens or hundreds of sibling stars. In such environments, gravitational encounters are frequent, and stars can capture or exchange companions. Nemesis could have been a captured brown dwarf, or red dwarf star, initially formed elsewhere but gravitationally bound to the Sun after a close encounter. Alternatively, Nemesis might be a primordial companion that formed alongside the Sun from the same molecular cloud, but later drifted outward into a distant, elongated orbit. Understanding the orbital mechanics of such a distant companion is crucial. Nemesis is hypothesized to orbit the Sun at a distance of around 1.5 light-years, roughly 50,000 astronomical units, AU, compared to Neptune's $30 orbit. At such a distance, Nemesis would complete one orbit every 26 to 30 million years, coincidentally matching the proposed periodicity of mass extinction events on Earth. The orbit would likely be highly elliptical, causing Nemesis to periodically plunge closer to the inner Oort cloud, disturbing trillions of comets in the process. These disturbances could send a cascade of comets hurtling toward the inner solar system, increasing impact risks on Earth and other planets. However, this scenario raises additional questions about orbital stability and survivability. The Sun's orbit around the galaxy and gravitational interactions with passing stars and molecular clouds could perturb Nemesis's orbit over time, possibly ejecting it from the solar system or altering its orbit enough to disrupt the periodic impact pattern. The dynamical stability of such a wide binary system across billions of years remains an area of active research, involving complex n-body simulations and long-term modeling. One compelling aspect of the Nemesis hypothesis is its link to the Oort Cloud, a vast, spherical shell of icy bodies enveloping the solar system at distances between 2,000 and 100,000 Australian dollars. The Oort Cloud is thought to be the source of long-period comets, which have orbits lasting thousands or millions of years. Disturbances from a passing star or companion like Nemesis could destabilize these distant cometary orbits, sending them spiraling inward. In fact, the observed flux of long-period comets entering the inner solar system is not constant but varies over time, possibly reflecting such periodic perturbations. Despite its allure, the Nemesis hypothesis is challenged by the increasing sensitivity and coverage of modern infrared sky surveys. Instruments such as NASA's Wide Field Infrared Survey Explorer, WISE, have scanned the entire sky in infrared wavelengths, capable of detecting objects as cool and faint as brown dwarfs, and even some large planets at great distances. The absence of any clear detection of a Nemesis-like object in these surveys places stringent limits on its size, brightness, and distance. If Nemesis exists, it must be smaller or colder than originally hypothesized, or perhaps on a more complicated or transient orbit. Another fascinating development is the investigation into comet showers and their possible correlations with extinction events. While some studies find weak evidence of periodicity, others dispute these claims, attributing apparent patterns to random clustering or statistical artifacts. The paleontological record itself is incomplete and subject to dating uncertainties, making it difficult to confirm any strict periodic cycle. Nonetheless, the possibility of external astrophysical drivers influencing Earth's biological history remains a tantalizing scientific frontier. If Nemesis or a similar object is real, it also raises concerns about the long-term future of life on Earth. Catastrophic impacts from comet showers could pose existential threats, wiping out dominant species and reshaping ecosystems. While humans now possess technologies to detect and potentially deflect near-Earth objects, understanding distant triggers for comet influxes would be vital for planetary defense strategies on multi-million-year timescales. In the wider cosmic context, the Nemesis idea intersects with studies of rogue planets, wandering brown dwarfs, and free-floating stars. Our galaxy likely contains billions of such objects, roaming the interstellar medium, some occasionally passing near star systems. These encounters could perturb Oort clouds or comet belts, suggesting that extinction-triggering events might not require a bound companion star but could also result from random stellar flybys. Further scientific efforts aim to characterize the outer solar system's architecture more comprehensively. Projects targeting the Kuiper belt, scattered disk, and inner Oort cloud continue to discover unexpected populations of small bodies with peculiar orbits, hinting at gravitational influences from unseen massive bodies. The existence of Planet 9 is particularly intriguing, as its gravitational fingerprint is detectable through the clustering of distant trans-Neptunian objects. The quest to find Nemesis is not just a search for a star, it is a journey into understanding the dynamic relationships between celestial mechanics, solar system evolution, and life on Earth. Each new discovery about the solar system's distant frontier informs our knowledge of its past and potential futures. On a broader cultural and philosophical level, Nemesis embodies humanity's perennial fascination with cosmic forces beyond our control. It reminds us that the universe operates on scales far grander and more mysterious than daily life suggests. The possible existence of a dark companion star nudging comets and shaping the fate of life blurs the boundary between cosmic and biological history. Scientific curiosity continues to propel the search for Nemesis, fueled by advances in technology and data analysis. Upcoming missions and observatories promise deeper, more detailed views of the cold, distant reaches where Nemesis might hide. These include the James Webb Space Telescope, with its exceptional infrared sensitivity, and future all-sky surveys planned for the next decades. As researchers probe these mysteries, they also refine models of comet dynamics, star formation, and solar system origins. The interplay of theory and observation gradually sharpens the picture, ruling out some possibilities while opening new avenues for exploration. The story of Nemesis exemplifies the scientific method's iterative nature, where hypotheses are proposed, tested, revised, or discarded based on evidence. It also illustrates how the pursuit of knowledge often leads to unexpected discoveries, reshaping our understanding of reality. While the existence of Nemesis remains unproven, its hypothesized effects on Earth's history and cosmic environment continue to inspire research, debate, and imagination. It stands as a testament to the complex, interconnected cosmos we inhabit, where distant stars may influence life's destiny in subtle but profound ways. The mystery of Nemesis invites us to look upward and outward, pondering the dark corners of our solar system and the universe beyond. It challenges us to develop ever more sensitive instruments, clever algorithms, and comprehensive theories to unveil the hidden architecture of our cosmic neighborhood. In this pursuit, we deepen our grasp of the forces shaping planetary systems, the hazards lurking in space, and the delicate balance sustaining life on Earth. Nemesis, whether real or myth, serves as a powerful catalyst for inquiry, reflection, and wonder. It compels us to consider our place not only in the solar system but within the vast, dynamic galaxy, where stars, planets, comets, and life itself are linked in an ongoing cosmic dance. The story of Nemesis is part of that dance, a shadowy partner whose steps we are only beginning to discern. As we continue this quest, one truth remains clear: the universe is full of mysteries, and each one holds the potential to reshape how we see ourselves and our cosmic environment. Nemesis challenges us to remain vigilant, curious, and open to the unexpected, reminding us that even the darkest companions may hold keys to understanding the past and future of our planet. Delving further into the implications of Nemesis, it is important to consider how its presence might affect not only the solar system's architecture but also the very processes that govern planetary habitability and the evolution of life. If Nemesis does indeed perturb cometary orbits on a roughly 26 million year cycle, leading to increased bombardment of the inner solar system, the consequences could be staggering. Such comet showers could induce periodic climate upheavals, triggering rapid shifts in Earth's environment that challenge ecosystems to adapt or perish. This cyclical external influence might explain the episodic nature of mass extinctions and subsequent bursts of evolutionary innovation seen throughout the fossil record. At the same time, Nemesis's hypothetical orbit through the Oort Cloud and beyond could also contribute to the redistribution of icy bodies, seeding the inner solar system with volatile compounds essential for life. Comets are known to carry water, organic molecules, and complex carbon compounds, and their impacts have been proposed as a source for delivering these ingredients to early Earth. In this sense, Nemesis might play a dual role, both as a harbinger of destruction and as a catalyst for the delivery of life's building blocks, embedding it deeply within the narrative of Earth's biological history. The search for Nemesis intersects with broader questions about the frequency and impact of catastrophic events in the galaxy. If binary stars like Nemesis are common, and their distant companions regularly send cometary debris inward, then other planetary systems might experience similar cycles of bombardment and extinction. This has profound implications for astrobiology and the search for extraterrestrial life. Life on other worlds might be repeatedly reset by these cosmic perturbations, influencing the evolution of complexity and intelligence elsewhere in the universe. Technological advances have vastly improved our capacity to probe the distant reaches of our solar system, the Oort Cloud, and the surrounding galactic environment. Surveys conducted with infrared space telescopes, such as WISE and Spitzer, have mapped large portions of the sky, identifying numerous brown dwarfs and rogue planets. The lack of a confirmed nemesis thus far suggests that if it exists, it must be extremely faint, cold, and possibly smaller than previously thought, perhaps even a massive planet rather than a star. Alternatively, Nemesis might be on a highly inclined or eccentric orbit, placing it in regions of the sky that are challenging to observe, or its orbital period could be longer or more irregular than the classic 26 million year hypothesis. Further complicating the picture is the fact that the gravitational influence of Nemesis could extend beyond merely disturbing cometary orbits. It might also affect the orbits of distant trans-Neptunian objects, subtly sculpting the edge of the Kuiper belt and influencing the distribution of dwarf planets like Sedna and Eris. Some astronomers speculate that what we attribute to Planet 9, another hypothetical massive body proposed to explain clustered orbits of distant icy objects, could actually be related to or compounded by the presence of Nemesis. These overlapping hypotheses highlight the complexity of disentangling the myriad forces shaping our solar system's outer frontier. Astrophysical models of Nemesis's orbit and its long-term stability rely heavily on computer simulations, which incorporate gravitational interactions not only with the Sun but also with the galactic tide and passing stars. These simulations indicate that a companion star on such a wide orbit could persist for billions of years, but might occasionally undergo dramatic orbital changes or even be stripped away from the Sun due to gravitational encounters with other stars in the Milky Way. The chaotic nature of these interactions makes the precise prediction of Nemesis's position and orbit extraordinarily difficult, underscoring the challenge astronomers face in confirming or disproving its existence. Despite these uncertainties, the Nemesis hypothesis has inspired a wealth of interdisciplinary research, spanning astronomy, geology, paleontology, and planetary science. By analyzing extinction patterns, impact crater records, and isotopic anomalies in sediments, scientists attempt to correlate terrestrial events with potential astrophysical triggers. Similarly, the study of comet populations and their orbital distributions sheds light on the dynamics of the solar system's distant reservoirs of icy bodies. This collaborative approach exemplifies the interconnectedness of cosmic and Earth sciences in unraveling our planet's deep history. Philosophically, Nemesis raises profound questions about fate and randomness in the cosmos. Is life on Earth a delicate candle flickering in a turbulent cosmic storm, vulnerable to distant stellar companions? Or do these periodic catastrophes represent an intrinsic rhythm, a cosmic cycle that shapes evolution's path? The answers remain elusive, but contemplating Nemesis encourages a humbling perspective on our place in the universe. Looking ahead, the ongoing development of next-generation observatories will continue to refine our understanding. Telescopes like the Vera C. Rubin Observatory are poised to revolutionize time-domain astronomy, tracking transient events and distant objects with unprecedented detail. Meanwhile, space missions targeting the outer solar system and the Oort Cloud region may provide direct observational data to test Nemesis's influence. Coupled with improvements in data analysis techniques, including machine learning and artificial intelligence, these tools promise to uncover subtle signatures of unseen companions. The search for Nemesis exemplifies humanity's quest to illuminate the darkest corners of our cosmic neighborhood. Whether this elusive companion star exists or not, its legacy endures in the questions it raises and the mysteries it compels us to explore. It reminds us that the solar system is not a static, isolated system but a dynamic arena shaped by complex gravitational dances, where even distant, invisible actors can influence the fate of life. As we deepen our gaze into the cosmos, we reaffirm the scientific spirit, a relentless pursuit of truth guided by evidence, imagination, and curiosity. The story of Nemesis is a chapter in that grand endeavor, inviting us to look beyond the familiar and embrace the unknown, knowing that every mystery solved leads to new horizons and deeper wonder. The quest to understand Nemesis also challenges the very limits of astronomical detection. Because Nemesis is hypothesized to be a dim, cold object far beyond the reach of visible light telescopes, it forces astronomers to rely on indirect evidence and observations in other parts of the electromagnetic spectrum. Infrared observations are particularly crucial, as objects like brown dwarfs and cool red dwarfs emit most of their energy in these wavelengths. Space-based infrared observatories like the Wide Field Infrared Survey Explorer, WISE, have conducted all-sky surveys that have ruled out many possible candidates for Nemesis, yet a definitive discovery remains elusive. This gap between theoretical necessity and observational confirmation fuels ongoing debate and research. Nemesis's potential role in triggering comet showers also ties into the broader topic of the Oort Cloud, a vast, spherical shell of icy bodies enveloping our solar system at a distance of roughly 50,000 to 100,000 astronomical units. The Oort Cloud is believed to be a remnant of the early solar system, containing trillions of comets and other primordial objects. A disturbance by a passing star or a companion star like Nemesis could send these icy bodies plunging into the inner solar system, increasing the likelihood of impacts on planets, including Earth. Understanding this dynamic helps explain not only extinction events but also the influx of new materials that could have helped spark life or modify planetary environments over time. Interestingly, the Nemesis hypothesis emerged as a potential solution to a puzzling pattern observed in the fossil record: the apparent periodicity of mass extinctions every 26 to 30 million years. Early paleontologists and astronomers noticed a rough rhythm in these catastrophic die-offs, raising the question, could there be an astronomical cause behind these terrestrial events? The idea of a dark companion star disturbing cometary orbits offered a tantalizing explanation, linking cosmic phenomena with Earth's geological and biological history in a profound way. However, this periodicity is not without controversy. Some researchers argue that the evidence for regular extinction cycles is inconclusive, or that other mechanisms, such as volcanic activity, plate tectonics, or climate change, better explain these patterns. Additionally, the exact timing and magnitude of extinction events do not always align neatly with the proposed Nemesis cycle. This ambiguity highlights the complexity of Earth's history and the interplay of multiple factors influencing life's trajectory. Another angle to consider is the broader context of binary star systems in our galaxy. Binary and multiple star systems are common. In fact, a significant percentage of stars exist in such configurations. However, most binary companions are relatively close to their primary stars. A distant companion like Nemesis, on an orbit of tens of thousands of astronomical units, would be unusual but not impossible. The stability of such an orbit over billions of years, subject to galactic tides and encounters with passing stars, presents a dynamic puzzle that researchers continue to explore through simulations and observations. If Nemesis does exist, its discovery would not only revolutionize our understanding of the solar system, but also shed light on the gravitational environment of the Sun within the Milky Way. It would offer a unique laboratory to study the interactions between a star, its distant companion, and the cloud of small bodies that inhabit the outskirts of the system. This knowledge could also inform models of planet formation, solar system evolution, and the potential habitability of planets in binary systems elsewhere in the galaxy. The cultural impact of the Nemesis hypothesis is also worth noting. It has inspired a range of scientific papers, popular science books, documentaries, and even speculative fiction. The concept of a hidden dark star lurking in the shadows of our solar system taps into deep human fascination with cosmic mysteries and the unknown. It symbolizes the unseen forces that shape our existence, reminding us that our apparent cosmic neighborhood might harbor secrets yet to be uncovered. From a methodological perspective, Nemesis exemplifies the scientific process, a hypothesis born from observation, tested through data collection and analysis, challenged by new evidence, and refined or discarded accordingly. The scientific community's skepticism, healthy debate, and continuous pursuit of evidence demonstrate the rigor and self-correcting nature of science. Even without direct detection, Nemesis remains a valuable concept that drives inquiry and innovation. Looking to the future, upcoming missions and technologies promise to enhance our ability to detect faint, distant objects. The James Webb Space Telescope, with its advanced infrared capabilities, and the Vera C. Rubin Observatory, which will scan the sky repeatedly, may uncover new objects or reveal subtle patterns hinting at a companion star's presence. Advances in computational modeling will also allow more precise simulations of the solar system's dynamics and interactions with the galactic environment, potentially confirming or refuting the Nemesis hypothesis with greater confidence. Moreover, the study of Nemesis intersects with other emerging fields, such as planetary defense. Understanding the sources and dynamics of potentially hazardous objects informs strategies to protect Earth from future impacts. If a companion star periodically sends cometary bodies toward the inner solar system, monitoring and predicting such events become critical for long-term planetary safety. Nemesis remains one of the most intriguing and debated mysteries in modern astronomy and planetary science. Its hypothetical existence bridges disciplines, linking celestial mechanics, paleontology, astrobiology, and earth sciences. Whether or not Nemesis is eventually found, The search itself drives scientific progress and enriches our understanding of the delicate interplay between cosmic forces and life on Earth. The story of Nemesis invites us to keep looking up, embracing the unknown, and recognizing that even the darkest, most elusive shadows in the universe may hold the key to unraveling our past and safeguarding our future. Exploring the intricacies of the Nemesis hypothesis further, one must also consider the evolutionary implications for life on Earth if such a cosmic companion indeed influences mass extinctions. Life's history is marked by periods of catastrophic loss followed by rapid diversification, events often called radiations. If Nemesis's periodic disturbances are real, they could represent a cosmic metronome, setting the tempo for evolution by periodically clearing ecological niches through extinction and opening avenues for new life forms to emerge and thrive. This cosmic rhythm might have shaped the trajectory of biodiversity, pushing life to innovate, adapt, and evolve in response to cycles of destruction and renewal. From a more technical standpoint, the mechanisms by which Nemesis could perturb the Oort Cloud are fascinating. The Oort Cloud, while gravitationally bound to the Sun, exists at distances so great that its outermost objects are only loosely held, making them susceptible to external gravitational nudges. The approach of Nemesis during its orbit could cause subtle gravitational ripples, dislodging comets from stable orbits and sending them hurtling inward. The timing, magnitude, and frequency of these perturbations depend on Nemesis's mass, orbital shape, and distance. Simulating these complex interactions requires sophisticated computer models that factor in the Sun's motion through the galaxy, tidal forces from the Milky Way, and encounters with passing stars. Despite the challenges, these simulations have produced intriguing results. Some models suggest that a Nemesis-like companion with a highly elliptical orbit could cause comet showers aligned roughly with the hypothesized extinction periodicity. Others indicate that the cumulative gravitational influence of multiple nearby stars and molecular clouds could produce a similar effect, complicating efforts to isolate Nemesis as the sole culprit. This underscores the difficulty of disentangling multiple overlapping influences in a dynamic galactic environment. It is also worth noting that the discovery of objects like Sedna and other detached trans-Neptunian objects has reignited interest in distant solar system companions. These bodies have orbits that cannot be easily explained by the known planet's gravitational pull, implying the presence of one or more unseen massive objects influencing their paths. While some researchers attribute these orbital peculiarities to a hypothetical Planet 9, others speculate that Nemesis or a similar companion could contribute to this gravitational shaping. This ambiguity reveals how much there still is to learn about our solar system's outskirts and the possible residents therein. Moreover, the potential impact of Nemesis on Earth's climate and geology extends beyond comet impacts. If Nemesis's orbit periodically brings it closer, even slight increases in solar radiation or tidal forces could subtly influence Earth's climate systems. Though these effects would be minor compared to the Sun's output, over geological timescales, even slight perturbations might compound, influencing glacial cycles or volcanic activity. While such effects remain speculative, they illustrate the interconnectedness of cosmic and terrestrial phenomena. From an observational perspective, advances in astrometry, the precise measurement of stars' positions and motions, offer hope for detecting Nemesis or similar companions. Missions like Gaia have mapped over 1 billion stars with unprecedented precision, providing data that can reveal subtle wobbles or gravitational effects indicative of unseen companions. While Gaia's primary targets are more distant stars, its data has improved understanding of the solar neighborhood's dynamics, constraining possible locations for Nemesis-like objects. The philosophical and existential implications of Nemesis are profound as well. If our solar system harbors a dark companion that influences Earth's biological history, it underscores how life is subject to cosmic forces beyond our control. It invites reflection on humanity's vulnerability and resilience, the contingency of existence, and the delicate balance required for complex life to persist. In this light, Nemesis symbolizes the invisible threads that bind life to the cosmos, threads woven from gravity, time, and chance. Furthermore, the interplay between Nemesis and human curiosity demonstrates science's power to transform speculative ideas into testable hypotheses. From an initial observation of periodic extinction patterns, scientists formulated a bold theory linking Earth to a hidden cosmic companion. Though still unconfirmed, this hypothesis has catalyzed advances in astronomy, planetary science, and paleontology, driving technological innovation and interdisciplinary collaboration. This journey exemplifies the iterative nature of scientific progress, where questions often lead to new horizons rather than definitive answers. In addition, the Nemesis story highlights the importance of humility in scientific inquiry. The vast scales of space and time involved challenge human perception and demand rigorous skepticism. The search for Nemesis teaches us to balance imagination with evidence, to remain open to unexpected findings, and to recognize that our understanding of the universe is always provisional and evolving. Considering the broader context of stellar companions, it is instructive to examine known examples of wide binary systems with distant companions. Some binary stars are separated by thousands or tens of thousands of astronomical units, bound by weak gravitational ties but stable over long periods. Studying these systems informs expectations about Nemesis's possible properties and orbital behavior, helping to refine search strategies and interpret data. The influence of the Milky Way galaxy itself also plays a critical role in shaping Nemesis's orbit. The Sun orbits the galactic center roughly every 230 million years, passing through different regions of varying stellar density and gravitational forces. These galactic tides can alter the orbits of distant companions and objects in the Oort Cloud, potentially triggering comet showers independently or in concert with Nemesis's effects. This galactic environment adds another layer of complexity and richness to the story of Nemesis. Moreover, the study of impact craters on Earth and the Moon provides a complementary window into the history of comet and asteroid bombardment. Radiometric dating of craters reveals clusters of impacts that may correspond to periods of increased comet activity, offering indirect evidence of external perturbations. While many craters are linked to asteroid impacts, some larger events could be attributed to comets, supporting the notion of periodic influxes of these icy bodies potentially linked to Nemesis. The Nemesis hypothesis also intersects with the emerging field of planetary defense, which seeks to identify and mitigate potential impact threats. Understanding the sources and triggers of comet showers is essential for assessing long-term risks and developing strategies to protect Earth. If Nemesis or similar companions periodically increase impact risks, monitoring the outer solar system becomes even more critical for planetary safety. At the cultural level, Nemesis has captured the imagination of writers, filmmakers, and the public. It serves as a potent symbol of unseen dangers lurking in the cosmos, blending scientific mystery with existential intrigue. This cultural resonance reflects humanity's enduring fascination with the stars and the search for meaning in the vastness of space. Looking ahead, the synergy of observational astronomy, computational modeling, and geological research promises to deepen our understanding of Nemesis and its potential role in solar system dynamics. As telescopes grow more powerful and data analysis techniques more sophisticated, we may soon uncover definitive evidence either confirming Nemesis's existence or explaining the observed phenomena through other means. The Nemesis hypothesis stands at the crossroads of astronomy, geology, biology, and philosophy, offering a rich tapestry of scientific and existential questions. Its investigation pushes the boundaries of knowledge, challenges assumptions, and inspires curiosity about the forces shaping our cosmic home and the fragile life it supports. The story of Nemesis is far from finished, inviting continued exploration and reflection as we seek to unveil the secrets hidden in the dark reaches beyond our sun. The ongoing pursuit to uncover Nemesis also acts as a beacon highlighting the limits of our current technological reach. Even with the most advanced telescopes and sensors, the vastness and darkness of space make detecting a faint, slow-moving object incredibly difficult. Unlike bright, nearby stars, Nemesis, if it exists, would likely be a cold, dim object, possibly a red or brown dwarf, that emits very little light in visible wavelengths. This means we must rely heavily on infrared observations, where such objects emit most of their radiation. The Wide Field Infrared Survey Explorer (WISE) mission, launched by NASA in 2009, scanned the entire sky in infrared and significantly expanded our knowledge of cool, dim objects in our solar neighborhood. Although WISE did not find a definitive candidate for Nemesis, its data has constrained the possibilities, ruling out many potential companion stars within certain distances. Despite this, the outer boundaries of our solar system remain largely uncharted. The Oort Cloud, home to billions of icy objects, extends up to 100,000 astronomical units (AU) from the Sun, far beyond the Kuiper Belt and the orbit of Pluto. This enormous, diffuse cloud is believed to be the source of long-period comets that occasionally enter the inner solar system. Because of its vast distance and sparse distribution, the Oort cloud is notoriously difficult to observe directly. Thus, any perturbation, such as that possibly caused by Nemesis, would be subtle and only indirectly evident through increased cometary activity. The idea of a cyclical pattern in mass extinctions that Nemesis might explain is both compelling and controversial. Some paleontologists and astronomers argue that mass extinctions, including the famous event that wiped out the dinosaurs 66 million years ago, seem to recur roughly every 26 to 30 million years. This periodicity suggests an external trigger, potentially an astronomical event, rather than purely terrestrial causes like volcanic activity or climate shifts. The Nemesis hypothesis posits that the gravitational influence of a companion star in a long, elliptical orbit disturbs the Oort cloud at regular intervals, sending swarms of comets hurtling inward. These comet showers would increase the probability of catastrophic impacts on Earth, triggering mass extinctions. However, this hypothesis has faced scrutiny. Some statistical analyses of extinction data find no strong evidence for strict periodicity, while others suggest the observed cycles could be artifacts of incomplete fossil records or dating uncertainties. Moreover, some mass extinctions do not coincide neatly with the proposed intervals. Despite these challenges, the concept remains a fascinating lens through which to examine the interplay between cosmic forces and Earth's biological history. Another fascinating dimension of Nemesis lies in the broader context of binary and multiple star systems. Around half of all Sun-like stars in our galaxy exist as part of binary or multiple systems. These companions typically orbit much closer than the proposed distance of Nemesis, usually within a few hundred AU. The idea of a companion star orbiting tens of thousands of AU away is unusual but not unprecedented. Observations have revealed some extremely wide binaries, though their gravitational bonds are weak and easily disrupted by passing stars or galactic tides. Such fragility raises questions about whether a Nemesis-like star could maintain a stable orbit over billions of years, or whether it might be a transient visitor or a captured rogue star. If Nemesis does exist, discovering it would revolutionize our understanding of the solar system's architecture and dynamics. It would reveal a previously hidden component of our cosmic neighborhood, alter models of solar system formation, and shed light on the processes that shape comet populations and impact rates. This discovery would also emphasize the dynamic nature of our solar system, not a static collection of planets orbiting a solitary star, but a complex system influenced by a host of gravitational interactions extending far beyond the planets. From a cultural perspective, the Nemesis hypothesis has inspired myriad works of fiction, documentaries, and speculative science discussions. The notion of a hidden dark star lurking in the solar system's outskirts taps into humanity's fascination with mystery, danger, and the unknown. It also serves as a reminder of the limits of human perception and the vastness of the cosmos, where unseen forces may influence life on Earth in ways we are only beginning to understand. The scientific journey toward resolving the Nemesis question exemplifies the process of hypothesis, investigation, and revision fundamental to science. The hypothesis emerged from efforts to explain intriguing geological and biological patterns, sparked detailed observational campaigns and theoretical modeling, and has since faced tests and challenges with new data. This iterative cycle reflects science's self-correcting nature, where ideas are refined or replaced as evidence accumulates. Looking to the future, technological advances promise to enhance our ability to detect faint companions and distant solar system objects. Next-generation telescopes like the James Webb Space Telescope, JWST, with its powerful infrared capabilities, and the Vera C. Rubin Observatory, designed for wide-field sky surveys, will deepen our understanding of the solar system's periphery and the stellar neighborhood. These instruments may identify candidates for Nemesis or clarify the nature of distant gravitational influences, helping to resolve lingering uncertainties. Moreover, improving computational models allow scientists to simulate the long-term dynamics of the solar system and its interaction with the galactic environment more accurately than ever before. These simulations explore scenarios involving companion stars, galactic tides, and passing stars, offering insights into the complex gravitational ballet that shapes comet influxes and impact risks. In addition, the Nemesis hypothesis intersects with efforts in planetary defense. Understanding sources of potential impactors is critical for anticipating and mitigating threats to Earth. If Nemesis or similar phenomena periodically increase the flux of cometary bodies toward Earth, monitoring and preparedness become even more vital. This connection between cosmic dynamics and planetary safety highlights the practical importance of studying such theories. Philosophically, the Nemesis concept invites contemplation about humanity's place in the cosmos. It reminds us that life on Earth is vulnerable to forces far beyond our control, shaped by the movements of distant stars and icy bodies billions of kilometers away. This perspective evokes a mixture of humility and wonder, inspiring ongoing curiosity about the universe's mysteries. The search for Nemesis also underscores the value of interdisciplinary collaboration. Astronomy, paleontology, geology, physics, and computational science all contribute pieces to this complex puzzle. By integrating data and theories from multiple fields, scientists gain a more comprehensive understanding of the potential connections between cosmic phenomena and Earth's biological history. Furthermore, recent discoveries of unusual trans-Neptunian objects with highly elliptical orbits, such as Sedna, have invigorated discussions about the possibility of unseen massive objects influencing the solar system's outer reaches. While many scientists favor the existence of a Planet 9 to explain these orbital oddities, some have speculated whether Nemesis or another distant companion could also play a role. This ongoing debate highlights how much remains to be learned about the solar system's architecture. The dynamic galactic environment also complicates the Nemesis story. As the Sun orbits the Milky Way, it passes through regions of varying stellar density, molecular clouds, and galactic tidal forces. These environmental factors can perturb the orbits of distant solar system objects and potentially influence cometary activity. Understanding the interplay between Nemesis's orbit and the Sun's galactic journey is essential for interpreting the timing and frequency of extinction events. Additionally, geological records of impact craters on Earth and the Moon offer important clues. Dating of large craters reveals clusters of impacts that might correspond with periods of increased comet activity. While many such impacts can be attributed to asteroids, some may originate from long-period comets disturbed by external forces like Nemesis, adding another layer of evidence to consider. The Nemesis hypothesis also serves as a reminder of the importance of observational perseverance and technological innovation. The solar system's distant regions remain one of the least explored frontiers in astronomy. Future missions, both ground-based and spaceborne, equipped with more sensitive instruments, will continue to probe these remote areas, potentially revealing hidden companions or new classes of objects. The Nemesis hypothesis remains a captivating blend of scientific inquiry, cosmic mystery, and existential reflection. Whether ultimately proven or disproven, it continues to push the boundaries of our knowledge about the solar system, the galaxy, and the forces that shape life on Earth. The story of Nemesis encourages us to keep looking beyond the familiar, to embrace the unknown, and to appreciate the delicate dance of celestial mechanics that influences our past, present, and future. Continuing deeper into the enigmatic search for Nemesis, we must also consider the broader cosmic context in which such a companion star would exist. The Milky Way itself is a dynamic, ever-changing environment, where stars, gas, and dark matter interact in complex ways. The Sun, traveling through this cosmic ocean, experiences gravitational nudges from nearby stars and molecular clouds that can perturb the orbits of distant solar system objects, potentially mimicking or complicating the effects attributed to Nemesis. This interplay suggests that even if Nemesis does not exist, other galactic phenomena might similarly trigger comet showers and influence extinction cycles on Earth, blurring the lines between local and galactic causes. Expanding on the theoretical models, scientists use sophisticated n-body simulations to study how a distant companion star might influence the orbits of comets in the Oort Cloud. These simulations must account for gravitational interactions over millions of years, factoring in not only the companion's orbit but also perturbations from passing stars and the galactic tide. The resulting predictions can be compared with observed comet trajectories and timing of impact events to assess the viability of the Nemesis hypothesis. Such computational approaches have become increasingly powerful with advances in supercomputing, enabling more detailed and realistic models that refine our understanding of long-term solar system dynamics. The potential nature of Nemesis itself adds layers of intrigue. If it exists, it could be a red dwarf star, which is the most common type of star in our galaxy, small, cool, and faint compared to the Sun. Alternatively, Nemesis might be a brown dwarf, a substellar object too massive to be a planet but not massive enough to sustain hydrogen fusion like a star. Brown dwarfs emit primarily in the infrared, making them challenging to detect with traditional optical telescopes. The existence of brown dwarfs was confirmed only in the late 20th century, demonstrating how new discoveries can reshape astronomical paradigms and reopen questions about objects lurking unseen in our cosmic neighborhood. Further complicating the search is the possibility that Nemesis could be a rogue star or brown dwarf, captured by the Sun's gravity during the solar system's long journey through the galaxy. Such an object would have a highly elliptical and possibly unstable orbit, leading to irregular periods of disturbance in the Oort Cloud rather than a strict periodicity. This could explain why some extinction events and comet showers do not adhere perfectly to the predicted intervals. The capture scenario also raises fascinating questions about the interactions between stars and their environments, and the long-term stability of wide binary systems. The detection strategies for Nemesis have evolved alongside advancements in observational technology. Early searches relied on photographic plates and optical surveys, limited by the faintness and slow motion of any potential companion. The advent of infrared astronomy revolutionized the search by revealing cool objects invisible to optical telescopes. Missions like IRAS, Infrared Astronomical Satellite, 2MASS, 2-micron all-sky survey, and WISE have scanned the sky in infrared, identifying numerous brown dwarfs and distant solar system objects. Yet, despite these efforts, no definitive evidence of Nemesis has emerged, underscoring the challenges posed by its hypothetical characteristics. Intriguingly, some theories propose that Nemesis might not be a single star but a system of objects, such as a binary brown dwarf pair or a star with multiple substellar companions. This scenario could produce more complex gravitational effects on the Oort Cloud and a more erratic pattern of comet showers. Observing such systems at great distances remains difficult, but understanding their dynamics could provide insights into how wide binaries and multiple systems form and evolve, further enriching our knowledge of stellar astrophysics. The relationship between Nemesis and planetary defense efforts also warrants consideration. If a distant companion periodically perturbs cometary orbits, increasing the risk of impacts on Earth, then identifying and monitoring such threats becomes crucial for humanity's survival. This intersection of astronomy, planetary science, and disaster preparedness exemplifies how fundamental research can have profound practical implications. Efforts to catalog near-Earth objects, NEOs, improve impact prediction models, and develop mitigation strategies are vital components of this broader endeavor. From an astrobiological perspective, Nemesis raises questions about the role of cosmic events in shaping the evolution of life. Periodic mass extinctions, potentially linked to extraterrestrial triggers, have reset Earth's biological diversity multiple times, influencing the trajectory of evolution. Understanding these processes informs our search for life elsewhere, as similar dynamics could affect habitability on other planets in different stellar systems. The interplay between astronomy and biology thus enriches both fields and fuels curiosity about life's resilience and vulnerability in the cosmos. The cultural resonance of Nemesis extends beyond science into philosophy, literature, and art. The idea of a hidden cosmic force influencing life on Earth taps into deep human fears and fascinations with fate, destiny, and the unknown. Nemesis, named after the Greek goddess of retribution, symbolizes a celestial bringer of doom, reminding us of the precariousness of existence and the vast, often indifferent universe we inhabit. This symbolic power has inspired countless stories, films, and speculative works that explore themes of cosmic horror, survival, and discovery. As research continues, the boundaries between hypothesis and discovery blur, emphasizing the dynamic nature of scientific knowledge. The Nemesis story exemplifies how tentative ideas, grounded in observation and theory, drive exploration and debate, even when definitive answers remain elusive. This ongoing inquiry fuels technological innovation, interdisciplinary collaboration, and public engagement with science, highlighting the value of curiosity-driven research. Looking ahead, planned missions and telescopes promise to deepen our understanding of the solar system's outskirts. Projects like the Nancy Grace Roman Space Telescope and future infrared observatories will enhance sensitivity to faint, distant objects. Ground-based surveys with telescopes like the Vera C. Rubin Observatory will provide wide-field, time-domain data to detect slow-moving or variable objects. Combined with improved computational models and machine learning techniques, these tools may finally reveal or definitively exclude Nemesis's existence. Simultaneously, studies of other wide binary systems and isolated brown dwarfs inform expectations about what kinds of objects might lurk near our Sun. Comparing the Sun's neighborhood to other stellar environments helps contextualize the Nemesis hypothesis and understand the diversity of stellar companions. This comparative approach enriches astrophysics and clarifies how common or unique our solar system's configuration might be. The enigmatic Nemesis, whether real or imagined, remains a powerful focal point for exploring fundamental questions about cosmic influences on Earth's history. Its investigation challenges assumptions, pushes scientific frontiers, and inspires wonder about the hidden architecture of our cosmic home. Through this lens, we glimpse the profound interconnectedness of celestial mechanics, planetary evolution, and life itself. Thus, the tale of Nemesis is far from over. As new data arrive and theories evolve, the mystery persists, inviting us to keep searching, questioning, and marveling at the cosmos. It reminds us that even in an age of extraordinary knowledge, the universe holds secrets that continue to captivate the human spirit and expand the horizons of understanding. Delving even further into the enigma of Nemesis, it is crucial to recognize how its hypothetical existence challenges our perception of the solar system as a stable, isolated entity. Instead, it compels us to view our cosmic neighborhood as a dynamic and interactive environment, where the Sun itself may not be solitary but part of a subtle binary dance with a faint companion. Such a concept shifts paradigms in astronomy, inviting questions about how common such wide binaries might be and how they influence planetary systems' formation and evolution. One particularly intriguing aspect of Nemesis lies in the periodicity it allegedly introduces to extinction events. Studies of the fossil record suggest that mass extinctions on Earth might follow a cyclical pattern roughly every 26 to 30 million years. This observation sparked considerable interest because it implied the possibility of a regular astronomical trigger. If Nemesis exists with an orbital period in this range, its passage through or near the Oort Cloud could disturb comets, sending a barrage inward toward the inner solar system. Such bombardments could dramatically increase the likelihood of impacts on Earth, correlating with the fossil evidence for recurring mass die-offs. Yet, the precise nature of this periodicity is debated. Some researchers argue that the data are noisy or subject to sampling biases and that extinction events do not fit neatly into strict cycles. Others propose alternative explanations for the observed periodicity, such as the solar system's oscillation through the dense midplane of the Milky Way galaxy, where increased gravitational perturbations might induce comet showers independently of a companion star. This complexity illustrates how astrophysical hypotheses must be carefully tested against geological and paleontological data, requiring cross-disciplinary collaboration. In addition to perturbing comet orbits, a dark companion star like Nemesis could influence the orbits of trans-Neptunian objects, TNOs, and other distant bodies in the Kuiper belt and beyond. Some scientists speculate that peculiar orbital clustering observed among certain TNOs might be explained by gravitational effects from an unseen massive object, whether a planet-sized body, a brown dwarf, or a stellar companion. While some of these hypotheses focus on the so-called Planet 9, the possibility of Nemesis also remains part of this broader investigation into solar system architecture and dynamics. The hypothetical characteristics of Nemesis also pose observational challenges. Because it would likely be very faint, emitting most of its energy in the infrared spectrum due to its low temperature, it might evade detection by conventional optical surveys. Its slow motion against the background stars, combined with its great distance, further complicates discovery. Infrared surveys like the Wide Field Infrared Survey Explorer, WISE, have significantly constrained the parameter space for such objects, ruling out many candidates, but the search is not yet exhaustive. There remains a faint possibility that a very cool, low-luminosity companion lurks just beyond our current detection limits. Another consideration is that if Nemesis exists on a highly elliptical orbit, it might spend most of its time very far from the Sun, only periodically plunging closer to the inner solar system. This orbital behavior would produce intermittent perturbations, possibly explaining irregularities in comet showers and extinction timing. Such eccentric orbits, however, raise questions about long-term orbital stability. Over millions of years, gravitational interactions with passing stars, molecular clouds, or the galactic tide could significantly alter Nemesis's orbit, potentially ejecting it from the solar system or changing its perturbative effects. On a theoretical level, the Nemesis hypothesis intersects with the broader search for dark matter and dark objects in our galaxy. While Nemesis itself is unlikely to be composed of exotic dark matter, the idea of unseen massive bodies influencing visible matter resonates with efforts to understand the distribution of mass in the Milky Way. Discoveries of massive compact halo objects, machos, and other dark bodies have expanded the scope of astrophysics, revealing that much of the galaxy's mass remains invisible, shaping gravitational fields in subtle ways. Nemesis could be viewed as part of this hidden mass landscape. From the perspective of impact geology and planetary defense, understanding Nemesis's potential influence is vital. Impact events have shaped Earth's environment and biological evolution, from the extinction of the non-avian dinosaurs 66 million years ago to smaller, but still significant regional and global impacts. If Nemesis triggers periodic comet showers, it emphasizes the importance of monitoring long-period comets and understanding their orbital dynamics. It also underscores the need for international cooperation in developing impact mitigation technologies, such as asteroid deflection missions and early warning systems. The story of Nemesis also intersects with human imagination and cultural symbolism. Named after the goddess of retribution and balance, Nemesis evokes a cosmic justice or inevitable consequence, an unseen force that periodically reminds humanity of its fragility. This symbolism fuels a rich tradition of storytelling that blends science, myth, and existential reflection, prompting us to consider our place in a vast and sometimes threatening universe. Through literature, film, and art, the idea of Nemesis shapes narratives about survival, fate, and the boundaries of knowledge. Moreover, the search for Nemesis exemplifies the scientific method in action, a bold hypothesis arising from observed phenomena, subjected to rigorous testing, refinement, and sometimes rejection or modification. This iterative process drives progress and expands our understanding of the cosmos, even when initial ideas prove incorrect or incomplete. The Nemesis hypothesis has inspired extensive observational campaigns, theoretical modeling, and debates that have deepened knowledge of stellar companions, comet dynamics, and mass extinctions, regardless of the ultimate verdict on its existence. In the realm of technological advancements, future space missions and telescopes will dramatically enhance our ability to detect faint, distant objects. The James Webb Space Telescope, JWST, with its powerful infrared capabilities, may provide unprecedented insights into the outer solar system and nearby stellar environments. Ground-based observatories equipped with adaptive optics and large-scale surveys will complement these efforts, enabling more comprehensive sky coverage and higher sensitivity. Together, these tools will push the boundaries of discovery, potentially settling questions about Nemesis and revealing new cosmic phenomena. Furthermore, the exploration of Nemesis ties into broader themes of stellar and planetary system formation. The mechanisms by which wide binary stars form and evolve, the capture of rogue objects by stellar gravity, and the interactions within star clusters all inform our understanding of solar system history. If Nemesis exists, it might be a relic of the Sun's birth cluster environment, offering a window into the conditions that prevailed when our solar system formed 4.6 billion years ago. This connection between past and present deepens the scientific and philosophical significance of the hypothesis. The interplay between Nemesis and the Oort Cloud also illustrates the complexity of our solar system's boundary regions. The Oort Cloud itself remains largely theoretical, inferred from comet observations but never directly observed. Its vast, diffuse nature makes it difficult to study, yet it holds the key to understanding long-period comets and the solar system's interactions with the galaxy. Nemesis, if real, acts as a celestial gatekeeper, nudging these icy bodies inward and linking the distant outskirts to Earth's surface events in a cosmic chain of cause and effect. Scientific skepticism remains a cornerstone in evaluating the Nemesis hypothesis. While some evidence suggests periodicity and possible companion effects, alternative explanations and negative observational results temper enthusiasm. The lack of direct detection, combined with improvements in sky surveys that have ruled out many candidates, means that many astronomers now consider Nemesis unlikely or unnecessary to explain extinction cycles. Nonetheless, the hypothesis continues to inspire inquiry and is periodically revisited as new data and methods emerge. The debate around Nemesis also encourages interdisciplinary research, bridging astronomy, geology, paleontology, and climate science. Understanding how celestial events influence Earth's environment and life requires synthesizing diverse datasets and perspectives. This integration fosters novel insights and holistic models that transcend traditional disciplinary boundaries, illustrating the richness of modern scientific investigation. On a more speculative note, some researchers have considered the impact of Nemesis-like companions on exoplanetary systems elsewhere in the galaxy. If wide binary or multiple star systems commonly harbor distant companions that periodically perturb cometary or asteroid belts, then similar extinction cycles might occur on planets orbiting other stars. This possibility expands the implications of Nemesis beyond our solar system, influencing theories about the prevalence and stability of life in the universe. The enduring mystery of Nemesis underscores the vastness and complexity of the cosmos. Despite centuries of astronomical progress, fundamental questions remain unanswered, reminding us that exploration is an ongoing journey. Each hypothesis, discovery, and refutation brings us closer to a fuller understanding of the universe and our place within it, inviting continuous curiosity, humility, and wonder. As we continue to explore the concept of Nemesis, it is essential to appreciate how its hypothetical existence influences our understanding of cosmic hazard assessment. The possibility that a dark companion star could periodically send a flood of comets toward the inner solar system paints a picture of a universe where Earth's safety is not solely dictated by random chance, but may be governed by predictable celestial mechanics. If we could conclusively identify and track such a companion, it might open new avenues for forecasting periods of elevated impact risk, which could be critical for long-term planetary defense strategies. The potential mechanism behind Nemesis's influence involves gravitational perturbations that disturb the otherwise stable orbits of icy bodies residing in the Oort Cloud, an immense spherical shell of comets enveloping the solar system. The gravitational nudge from Nemesis as it moves through its orbit could dislodge these comets, sending them cascading inward. This process would generate comet showers that drastically increase the likelihood of impacts on planets like Earth, potentially triggering global ecological disruptions or mass extinction events. The concept that celestial mechanics can have direct consequences for life on Earth blurs the boundary between astronomy and biology in profound ways. In this context, the periodic mass extinction hypothesis provides a compelling framework for linking astronomy with the Earth's fossil record. By analyzing geological strata, paleontologists have identified several catastrophic die-offs that coincide with evidence of large impacts or environmental upheavals. The idea that these events follow a cycle harmonizes with the Nemesis hypothesis, offering a tantalizing clue that our planet's biological history might be written in the stars, quite literally. However, reconciling the data across disciplines remains challenging due to the inherent uncertainties in dating techniques and the complexity of extinction drivers. Moreover, the Nemesis hypothesis acts as a springboard for examining other potential causes of periodic extinction patterns. Some researchers argue that the solar system's oscillation up and down through the galactic plane could create periodic gravitational disturbances. The Milky Way's dense midplane, rich with molecular clouds and stars, exerts tidal forces on the solar system, possibly dislodging comets independently of any companion star. This alternative explanation challenges the uniqueness of Nemesis and invites more nuanced models that incorporate multiple astronomical factors influencing the influx of impactors. The discovery and study of wide binary systems elsewhere in our galaxy offer important context for understanding Nemesis. While close binaries are common, systems where a faint companion orbits thousands of astronomical units from the primary star are rarer but not unknown. Such configurations tend to be dynamically fragile, susceptible to disruption by passing stars or galactic tides over millions of years. This dynamical fragility makes the long-term survival of Nemesis more precarious, suggesting that if it exists, it may be a transient feature rather than a permanent fixture of our solar system. One of the profound challenges in the search for Nemesis is its predicted faintness. If Nemesis is a red or brown dwarf star, it would emit mostly infrared radiation, making it invisible to the naked eye and challenging to detect with traditional optical telescopes. Advances in infrared astronomy have dramatically improved our sensitivity to such faint objects, exemplified by missions like WISE, which scan the entire sky in infrared. These surveys have placed stringent limits on the presence of bright brown dwarfs or stars within thousands of astronomical units from the Sun, yet they have not definitively ruled out smaller, colder objects that could evade detection. The hypothetical orbit of Nemesis is thought to be highly elliptical, meaning it would spend long periods far from the Sun before swooping closer on a long, slow path. This orbital pattern is important because it dictates when and how the companion could perturb cometary orbits. At aphelion, Nemesis would be so distant and faint as to be nearly undetectable, but at perihelion, its gravitational influence could ripple through the Oort Cloud. Such an eccentric orbit could explain the irregular timing of comet showers and associated extinction events, adding layers of complexity to the prediction of impact hazards. Scientific interest in Nemesis has also influenced the development of theoretical models of stellar dynamics and solar system evolution. The interactions between Nemesis, the Oort Cloud, and passing stars involve intricate gravitational physics, including three-body problems and perturbation theory. These models help scientists understand not only the potential impact of Nemesis but also the broader dynamical environment in which the solar system resides. Simulations that incorporate the effects of galactic tides, stellar encounters, and hypothetical companions have refined our grasp of how comet flux varies over time. In parallel, the concept of Nemesis has inspired interdisciplinary research that bridges astronomy, geology, and biology. By correlating extinction events with astronomical data, scientists attempt to unravel whether extraterrestrial forces have periodically shaped the course of life on Earth. This interdisciplinary nexus exemplifies how scientific inquiry transcends traditional boundaries, fostering collaborations that generate holistic insights into the past and future of our planet. Beyond the scientific implications, Nemesis occupies a fascinating space in popular culture and speculative thought. Its very name, drawn from the Greek goddess of divine retribution, evokes a cosmic force of inevitable justice or punishment. This symbolism resonates with deep human fears and fascinations about extinction, fate, and the fragility of life. In science fiction and media, Nemesis serves as a powerful narrative device, embodying the unknown and the potentially catastrophic forces lurking in the darkness beyond our sun. From an observational standpoint, the continued improvement of sky surveys and telescopic technology holds promise for resolving the Nemesis question. Projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will provide unprecedented, high-cadence observations of the sky, enhancing our ability to detect faint moving objects across vast distances. These data could either reveal a hidden companion or provide even stronger constraints ruling out Nemesis-like objects within certain mass and distance ranges. The Nemesis hypothesis also encourages us to reconsider the processes that govern the formation and stability of wide binary systems. How such systems form and survive over billions of years involves complex interactions in dense stellar nurseries and subsequent gravitational encounters. If Nemesis is real, it might represent a fossil relic of the Sun's birth environment, offering clues about the early solar neighborhood and the mechanisms that shaped the solar system's architecture. Equally compelling is the question of Nemesis's potential role in shaping the environment for life on Earth. If comet showers triggered by Nemesis have contributed to mass extinctions, they have also indirectly influenced the evolutionary trajectory of surviving species. These catastrophic resets might have paved the way for new forms of life to emerge, driving diversification and adaptation. In this light, Nemesis is not merely a harbinger of doom, but also a potential agent of change and renewal in Earth's biological history. Further afield, the study of Nemesis-like phenomena may inform our understanding of exoplanetary systems. If wide binary companions and periodic comet showers are common in the galaxy, the stability and habitability of planets around other stars might be influenced by similar mechanisms. This perspective adds depth to the search for life beyond Earth, highlighting how cosmic dynamics shape planetary environments over geological timescales. Despite the wealth of hypotheses and investigations, the ultimate fate of the Nemesis theory remains uncertain. Its allure lies in its explanatory power for observed periodicities and extinction events, and its provocative suggestion that a hidden star influences Earth's destiny. Yet the lack of direct evidence, combined with competing models and negative search results, temper enthusiasm. The scientific community remains open but cautious, recognizing that extraordinary claims require extraordinary evidence. In the meantime, Nemesis continues to stimulate curiosity and inspire research. Its story exemplifies the spirit of scientific exploration, bold, imaginative, and grounded in observation and reason. As our tools and understanding improve, the enigma of Nemesis may either be unveiled or laid to rest, but its legacy in astronomy and planetary science endures. The search for Nemesis also reminds us of our limited perspective. The universe is vast and often obscured by darkness, both literal and metaphorical. What lies beyond the reach of our instruments today may become visible tomorrow, reshaping our understanding of the solar system and our place within it. The possibility of a dark companion star lurking unseen challenges us to keep looking, questioning, and expanding the horizons of knowledge. The Nemesis hypothesis urges humility in the face of cosmic scale and complexity. It warns us that even our seemingly stable home, the solar system, may harbor hidden threats shaped by forces beyond immediate perception. Yet, it also offers hope that by studying and understanding these forces, humanity can prepare for and perhaps mitigate future cosmic hazards. The ongoing quest to confirm or refute the existence of Nemesis touches on many fundamental questions about our cosmic neighborhood's architecture. If Nemesis exists, its discovery would force a profound reevaluation of the solar system's formation history and current dynamical state. We would need to consider how such a companion star managed to evade detection for so long, despite modern telescopes and infrared surveys that scan vast regions of the sky. This could imply that Nemesis is either extremely faint, possibly a very cold brown dwarf, or that its orbit takes it so far away for most of its cycle that it remains almost invisible to us, only periodically moving closer and becoming gravitationally influential. Astrophysicists have modeled a range of orbital parameters that Nemesis might have, showing orbits that can span tens of thousands of astronomical units, with orbital periods on the order of millions of years. These immense distances mean Nemesis's motion across the sky is extremely slow, complicating efforts to identify it via parallax or proper motion. Its gravitational influence on known solar system bodies might be subtle and masked by other forces, requiring extremely precise measurements to detect any perturbations. One compelling angle to the Nemesis story lies in the study of the Oort Cloud itself, a mysterious, distant shell of icy bodies thought to be the origin of long-period comets. Although the Oort Cloud has not yet been directly observed, its existence is inferred from the trajectories and dynamics of comets entering the inner solar system. The idea that a distant companion star could periodically destabilize this reservoir, sending comets inward, is intriguing because it links large-scale solar system dynamics with episodic events of great geological and biological consequence on Earth. Understanding how the Oort Cloud reacts to gravitational nudges from external sources, including hypothetical companions like Nemesis and passing stars, requires advanced simulations. Researchers run complex n-body simulations incorporating the gravitational forces of the Sun, planets, Nemesis, if present, and the galactic environment. These models reveal that even small perturbations can have cascading effects over millions of years, gradually changing comet orbits and increasing the likelihood of Earth-crossing trajectories. The consequences of such comet showers for Earth's environment and biosphere have profound implications. Impact events of sufficient size can cause immediate devastation through shockwaves, fires, and tsunamis, but they also trigger longer-term effects like atmospheric dust blocking sunlight, climate cooling or warming, and disruptions to photosynthesis and food chains. Some mass extinctions in Earth's history coincide with evidence of large impacts, including the famous Cretaceous Paleogene event that likely contributed to the demise of the non-avian dinosaurs. The search for Nemesis also intersects with efforts to catalog near-Earth objects, NEOs, and develop planetary defense initiatives. Knowing whether an additional stellar companion influences comet influx could improve predictive models for impact risks, allowing humanity to anticipate periods of increased danger and prepare accordingly. This cosmic perspective adds urgency to continuous sky surveys and the development of technologies to track and potentially deflect hazardous objects. Moreover, the concept of Nemesis invites reflection on the solar system's broader environment, the Milky Way galaxy. Our Sun orbits the galactic center roughly every 225 to 250 million years, moving through different regions of varying stellar density and gravitational influences. This galactic journey exposes the solar system to fluctuating tidal forces, increasing or decreasing the probability of comet disturbances. The interplay between a hypothetical Nemesis companion and galactic tides could create complex periodicities and comet showers, complicating efforts to decode Earth's extinction timeline. In addition to the scientific quest, the cultural impact of Nemesis is noteworthy. The idea of a hidden dark star lurking in the cosmic shadows captures the imagination, inspiring books, documentaries, and speculative fiction. Nemesis symbolizes humanity's enduring fascination with the unknown and the potential fragility of life on a tiny planet in a vast universe. This narrative can foster public interest in astronomy and planetary science, motivating support for scientific exploration and education. From a technological standpoint, the tools available to search for Nemesis have improved dramatically over recent decades. Space-based infrared observatories, ground-based wide-field surveys, and advances in detector sensitivity all enhance our ability to spot faint, distant objects. Future missions planned for the coming decades promise even greater precision and depth, potentially uncovering objects that have eluded detection until now. The hypothesis of Nemesis also encourages consideration of other dark or hidden companions in planetary systems, including brown dwarfs, rogue planets, and massive distant objects like the hypothesized Planet 9. These bodies, while difficult to detect, may play crucial roles in shaping the dynamical evolution of their systems. Nemesis could be just one example of a broader class of objects that influence planetary environments and impact rates on timescales relevant to life. Controversies surrounding the Nemesis theory highlight the iterative nature of scientific progress. Early excitement about Nemesis waned as surveys failed to find compelling evidence, but the underlying questions about periodic extinction patterns and comet showers remain open. This drives continued research into alternative explanations and refined models, underscoring how science advances by proposing, testing, and sometimes discarding hypotheses. The Nemesis saga exemplifies the challenges of studying phenomena at the limits of observation and time. It reminds us that many cosmic processes unfold over millions or billions of years, far beyond human lifespans and historical records. Understanding these processes demands patience, ingenuity, and the integration of data from diverse fields, from astrophysics to geology to paleontology. In contemplating Nemesis, we confront profound questions about our cosmic vulnerability and resilience. The prospect that a hidden star could influence Earth's fate invites humility and a deeper appreciation for the delicate balance that sustains life. It also inspires hope that through careful observation and understanding, we might one day predict or mitigate cosmic threats. Looking forward, the next decades of astronomical research hold promise for shedding light on Nemesis and related mysteries. Improved infrared surveys, deeper understanding of comet dynamics, and refined extinction chronologies will collectively sharpen our picture of how the solar system interacts with its environment. Whether Nemesis is confirmed or definitively ruled out, the journey of discovery enriches our knowledge and prepares us for future cosmic challenges. The story of Nemesis also speaks to humanity's enduring desire to find patterns and meaning in nature. The search for periodicities in extinction events, the quest for a hidden companion star, and the attempts to link cosmic phenomena to terrestrial life reflect a fundamental curiosity about our place in the universe. This quest continues to drive innovation, interdisciplinary research, and public engagement with science. Nemesis remains one of the most intriguing hypotheses in astronomy and planetary science, a hypothesis that blends the known and unknown, the visible and hidden, the astronomical and biological. Its investigation stretches the limits of observation and theory, challenges assumptions, and fuels our imagination about the cosmos and our fragile existence within it. The concept of Nemesis invites an exploration of celestial mechanics on scales both vast and subtle, scales where even a tiny nudge from a remote body can translate into life-altering consequences for planets orbiting hundreds or thousands of astronomical units away. If Nemesis exists, it is a cosmic ghost, an entity so distant, dark, and slow-moving that it might have evaded detection even by our most advanced telescopes. Yet its gravitational fingerprints could be all over Earth's history, hidden in the periodic rise and fall of life across geological epochs. One of the most tantalizing aspects of the Nemesis theory is how it blends rigorous scientific reasoning with a kind of mythological resonance. For millennia, humanity has looked up at the night sky and imagined unseen forces shaping our destiny. In some ways, Nemesis is the modern embodiment of that ancient instinct, an unseen force capable of periodically reshaping life on Earth, not through divine wrath but through orbital dynamics and gravitational mechanics. This duality, scientific plausibility and mythic allure, gives Nemesis a unique place in our cultural and intellectual landscape. Critically, the name, Nemesis, was not chosen lightly. In Greek mythology, Nemesis was the goddess of retribution, the force that ensures balance by punishing hubris. In the context of astronomy, the hypothetical companion star might not be vengeful by design, but its potential to deliver cyclical destruction invokes a deep psychological response. It suggests that the universe may harbor forces of balance and correction far beyond our immediate comprehension, forces that, every so often, sweep through the cosmos to reset the biological ledger of life on Earth. From a technical standpoint, searching for Nemesis pushes the boundaries of what is observable. A distant brown dwarf, cold, faint, and slowly drifting, would emit very little visible light, making it essentially invisible in optical surveys. Instead, astronomers must rely on infrared observations, where cooler objects like brown dwarfs emit more strongly. Missions like NASA's WISE, Wide Field Infrared Survey Explorer, were partially motivated by the hope of finding such hidden objects. Though WISE did not uncover Nemesis, it did reveal many previously unknown brown dwarfs, including a few closer than Proxima Centauri, highlighting just how little we still know about our cosmic backyard. Another challenge in identifying Nemesis is the complexity of background noise in the data. The sky is full of infrared sources, distant galaxies, interstellar dust, nearby stars, and even instrument noise. Distinguishing a slow-moving, cold object from this crowded background is like finding a shadow in a room already filled with them. Moreover, because Nemesis would move very slowly, its positional shift across years could be minute, demanding an enormous patience and computational precision to identify. Despite the setbacks in finding direct evidence for Nemesis, alternative explanations for periodic mass extinctions continue to be explored. Some researchers argue that the Sun's oscillation through the galactic plane could trigger comet influxes by disturbing the Oort Cloud. Others propose that interactions with molecular clouds or spiral arms in the Milky Way could periodically disrupt the outer solar system. These ideas, while not dependent on Nemesis, still support the core notion that astronomical phenomena can have long-term influences on Earth's biosphere. Further complicating the matter is the inherent uncertainty in the fossil record. The Earth is not a perfect archive. Geological processes can erase, distort, or obscure past events. The timing of mass extinctions is often debated, and aligning them to a precise 26 million-year pattern requires cautious statistical interpretation. What appears as periodic from one dataset might disappear when another is analyzed, or vice versa. This ambiguity leaves the door open for multiple hypotheses, including Nemesis, while simultaneously demanding skepticism and rigor. If Nemesis does exist and we eventually discover it, the implications for planetary science would be profound. We would gain a new understanding of solar system formation, perhaps learning that binary or multiple star systems are more common than once believed. Nemesis might offer clues to the dynamics of early solar nebulae, the stability of planetary orbits, and the long-term fate of comets and asteroids. It could even offer a new vantage point for studying the outer solar system, one that challenges our heliocentric assumptions and reveals a richer gravitational web extending into interstellar space. The psychological impact of discovering Nemesis would also be significant. For many, it would affirm a kind of cosmic fatalism, the idea that no matter how advanced our civilization becomes, we remain vulnerable to distant and uncontrollable forces. Yet, paradoxically, it could also empower us. Knowledge of such threats allows for preparation. It fuels innovation in planetary defense, inspires new missions to the outer solar system, and deepens our resolve to understand the universe more completely. Moreover, Nemesis is a reminder that the cosmos is still largely unmapped. While we have sent probes to the edge of the heliosphere and peered into the hearts of galaxies billions of light-years away, there remain vast swaths of near-Earth space, within a few 100,000 AU, that are largely unexplored. Objects like Nemesis, if they exist, could be silently orbiting in this dark domain, their presence hinted at only by statistical anomalies and ancient scars on the Earth's surface. Philosophically, the search for Nemesis also challenges our notions of time. Human lives are short, and even the span of recorded history is a mere blink in cosmic terms. But Nemesis operates on cycles of tens of millions of years. To grasp its potential impact requires a shift in perspective, an ability to think in epochs rather than generations, to perceive danger not in sudden calamity but in the slow turn of a celestial clock. This deep-time thinking is essential not just for astronomy but for addressing long-term risks like climate change, species extinction, and planetary defense. The persistence of the Nemesis hypothesis, even in the absence of concrete evidence, also speaks to a broader truth about science: that absence of evidence is not evidence of absence. Just because we haven't yet found Nemesis doesn't mean it isn't there. It simply means we haven't looked well enough, or that we've been looking in the wrong place, or with the wrong tools. As technology improves and our observational reach extends, what seems like myth today may become fact tomorrow. Importantly, the quest for Nemesis is not just about one star. It is about understanding the broader relationship between stellar companions and planetary systems. Many exoplanetary systems discovered to date include binary or even trinary stars. If Nemesis exists, the Sun may not be an exception but part of a much more common stellar architecture. This would force a recalibration of many models about planetary formation, stability, and habitability. In the grand tapestry of cosmic inquiry, Nemesis stands as both a question and a symbol. It challenges us to explore the unknown, to question the patterns of life and death on Earth, and to reconcile mythic fears with scientific evidence. Whether Nemesis turns out to be real or simply a powerful idea, its legacy will endure, as a testament to humanity's relentless curiosity and our determination to understand the forces that shape our place in the universe. Even if Nemesis remains a ghost in our celestial imagination, the scientific hunt it inspired has pushed forward important technologies, data analysis techniques, and ways of thinking about the solar system. Consider how many discoveries came as byproducts of searching for something else. Clyde Tombaugh was hunting for a predicted planet when he found Pluto. The WISE telescope, though it did not locate Nemesis, discovered hundreds of brown dwarfs and refined our knowledge of the structure and content of the local stellar neighborhood. In this way, Nemesis serves as both a compass and a muse, pointing science in new directions, even if the destination proves elusive. In the broader context of cosmic threats, Nemesis is but one face of the universe's indifference. Rogue planets, gamma-ray bursts, supernovae, and black holes all represent phenomena that could potentially impact Earth. Yet the idea of Nemesis is unique because it frames that threat as familiar and cyclical, a kind of cosmic heartbeat, pulsing destruction at intervals. This sense of rhythm, of a universe with periodic intentions, sets it apart from more random or singular catastrophic possibilities. If real, Nemesis would not only explain past extinctions but offer a chilling schedule for future ones. This leads naturally into the realm of prediction. If a consistent periodicity in mass extinction events is confirmed and tied to Nemesis, it might suggest we are able to forecast future windows of increased risk. Imagine knowing that, in a certain distant epoch, Earth will once again face a rain of comets or gravitational disruptions. It sounds like science fiction, but it's precisely the sort of long-range thinking that is increasingly necessary in a universe filled with slow-moving but inevitable dangers. The study of past catastrophes becomes, paradoxically, a tool for future survival. Yet this predictive power is predicated on the accuracy of the underlying data, which remains contentious. The supposed 26 million-year extinction cycle proposed by Ropp and Sepkoski has not gone unchallenged. Some scientists argue that extinction events are better explained by terrestrial mechanisms, volcanic activity, climate shifts, sea level changes, rather than extrasolar disruptions. The difficulty lies in separating correlation from causation. Just because comet showers and mass extinctions may coincide does not mean one causes the other. This ambiguity leaves Nemesis suspended between two realms, the plausible and the speculative. Still, the theory refuses to die. It endures not just because of data, but because of its elegance. It offers a single, sweeping explanation for multiple biological mysteries. In science, such elegance is seductive, but it can also be misleading. Reality is often messier than our models. Nevertheless, the persistence of Nemesis in scientific literature shows the value of bold hypotheses. Even if disproven, they catalyze inquiry, challenge assumptions, and refine our understanding of nature. Nemesis may not be a real object, but it is a real idea, and one that continues to shape discourse. Technologically, the future holds promise for a more decisive answer. With the development of more sensitive infrared instruments, larger sky surveys, and possibly even gravitational wave detectors that can track slow, massive objects, we may finally close the case. Projects like the Vera C. Rubin Observatory, formerly LSSD, will deliver unprecedented time-domain surveys of the night sky. These may catch the slow drift of a hidden object across years or decades of observation. Similarly, future space-based observatories focused on deep infrared detection could pinpoint the thermal signature of something as elusive as Nemesis. In parallel, our growing understanding of the Oort Cloud, the vast shell of icy objects surrounding the solar system, will also provide critical clues. If Nemesis exists, its gravitational influence should leave subtle signatures in the distribution, alignment, or eccentricities of these distant bodies. Some researchers have proposed that a different object, often dubbed Planet 9, could be shaping the outer solar system in similar ways. Intriguingly, the discussion of Planet 9 sometimes overlaps with that of Nemesis, though the two ideas originated from different lines of reasoning. Planet 9, if real, would likely be a super-Earth located hundreds of AU from the Sun, far closer than Nemesis would need to be. But both theories speak to an uncharted region of the solar system, a wilderness still waiting to be explored. Whether it's a distant planet, a dark star, or something entirely unexpected, the outer solar system remains one of the most tantalizing frontiers of modern astronomy. It's a place where the Sun's influence fades, where the fabric of the solar system blends into interstellar space, and where hidden companions may lurk unseen. This leads to a philosophical contemplation. What if the solar system was never a neat, singular construct? What if our image of the Sun as a lone monarch is merely a product of human-centric perspective and technological limits? As we uncover binary systems throughout the galaxy, many with planets of their own, it becomes increasingly likely that our solar system is the exception, not the rule. Nemesis, if discovered, would reset that narrative. It would place our Sun among the ranks of dual star systems and shift our understanding of how planetary systems evolve. Beyond astrophysics, the idea of Nemesis also stirs the imagination in fields like geology, paleontology, and even mythology. The rhythmic pulses of extinction events may correlate with mass sedimentation patterns, changes in global temperature, and ancient biological turnovers. In this sense, Nemesis becomes a multidisciplinary mystery. It demands collaboration between astronomers, geologists, biologists, and historians to piece together its puzzle. The notion that a dark star could have influenced the rise and fall of species on Earth brings a cosmic dimension to the study of life and death. In literature and art, Nemesis also finds resonance. It is a story element worthy of ancient epics, a dark twin bringing ruin in cycles. It echoes in tales of cosmic rebirth, of civilizations rising and falling with the tides of the heavens. Its metaphorical power enhances its scientific allure. The thought that something could exist just beyond the veil of light, shaping our fate in silence, is haunting. It inspires not only inquiry but awe, a humbling reminder of how much we still do not know. Meanwhile, the Nemesis hypothesis continues to evolve. Some versions suggest it may not be a star at all but a massive planet, a failed star, or even a small black hole. Each variation brings new implications, from how it might have formed to how it would interact with the Sun. Some researchers even explore exotic possibilities, like Nemesis being a relic of primordial dark matter or a capture from another star system. These ideas, while highly speculative, demonstrate the flexibility and richness of the mystery surrounding Nemesis. Indeed, every step toward resolving the Nemesis enigma reveals more about the nature of science itself. It shows how progress often comes not from certainty but from chasing the unknown. The search for Nemesis embodies the essence of exploration, a journey into darkness with only faint clues to guide us. It is the kind of quest that defines humanity's relationship with the cosmos, inquisitive, imaginative, and endlessly persistent. Whether Nemesis is discovered or not, it will leave a legacy. It has prompted decades of investigation, inspired new tools and methods, and challenged the boundaries of multiple disciplines. It has forced us to confront the fragility of life on Earth and the vast, often invisible, forces that shape it. And perhaps most importantly, it has reminded us that in the silence of space, not all threats are loud. Some move slowly, in shadow, and yet may hold the power to transform everything. The mystery of Nemesis remains one of the most captivating intersections between astronomy, paleontology, and human curiosity. It compels us to peer into the distant reaches of the solar system with questions not only about what is out there, but about what has already transpired on Earth because of what might lie beyond the light. Nemesis is more than a theory. It is a framework that forces scientists and thinkers alike to confront the possibility that our planet's fate has always been tied to celestial mechanisms hidden just out of reach, mechanisms that may have operated long before we even knew how to name the stars. If Nemesis were ever to be confirmed, it would fundamentally alter our understanding of solar system architecture. It would mean revising orbital dynamics, stellar classification, and even planetary formation theories. The realization that the Sun might have a distant, cold, and nearly invisible companion would upend one of our most basic cosmic assumptions, that our solar system is a singular star system. In fact, This realization would bring us more in line with the rest of the galaxy, where binary or even trinary systems are not unusual. What was once thought unique might turn out to be anomalous only in our limited perception. This raises important implications for exoplanetary science. If binary systems like the hypothetical Sun-Nemesis pair can support complex planetary systems, then we must consider how such configurations affect habitability, orbital stability, and the potential for life. Could Nemesis-like stars and other systems be delivering comets to their inner planets, sparking extinction events or, conversely, seeding those planets with the raw materials of life? Might Nemesis-type stars be agents not just of destruction, but of genesis? These questions link Earth's ancient past with the broader tapestry of life across the galaxy. Another fascinating layer of the Nemesis discussion is how it resonates with human myths and psychological archetypes. The idea of a hidden destroyer, one that emerges periodically to reset the world, echoes in countless cultural narratives. Carl Jung might say that Nemesis represents a kind of archetypal shadow, ever-present, barely seen, yet deeply influential. It is the invisible twin of our known cosmos, the necessary balance to the order we perceive. These mythic parallels, while not scientific evidence, do suggest that the human mind is attuned to seek patterns even in chaos, and to assign meaning to celestial rhythms. And rhythm is central to this theory. The cyclical nature of extinction, hinted at in fossil records, suggests that life on Earth may be dancing to the beat of a distant drummer, one we cannot see. Whether that drummer is Nemesis, or another undiscovered mechanism, remains to be determined. But the allure of periodicity is difficult to ignore. Life emerges, flourishes, and is culled back, sometimes violently, before the process begins anew. Nemesis offers a potential cosmic metronome for this biological symphony, even if the sheet music remains mostly illegible. Critics, however, are right to question this periodicity. After all, correlation is not causation, and geological timelines are fraught with uncertainty. Fossil dating, crater aging, and climate proxies all come with margins of error that can obscure real patterns or create illusory ones. Yet, the fact that the periodic extinction hypothesis has endured, despite its controversies, speaks to a deeper instinct that nature, while chaotic, may still operate on recurring principles. If those principles are influenced by astronomical cycles, then Nemesis remains a valid, if unconfirmed, candidate for further exploration. Moreover, in the absence of concrete evidence, the debate over Nemesis illustrates the power of negative results. Though WISE and other infrared surveys have not yet located such a body, their null results have narrowed the range of possibilities. Each failed attempt brings us closer to certainty, either by ruling Nemesis out or by refining our expectations of where and how it might be found. This is science at its best, not merely affirming what is known, but systematically dismantling what is not. Even if Nemesis is never discovered, the hypothesis has had the valuable side effect of spurring new scientific techniques. It has encouraged the development of wide-field infrared observation, refined dynamical models of the solar system, and led to sophisticated simulations of long-term orbital perturbations. In this sense, Nemesis has already served a purpose, much like the luminiferous ether once did for physics. Even disproven, it moved the field forward. Yet the question lingers, could we have missed it? Could Nemesis be hiding in some blind spot, masked by the galactic plane's density or simply too faint for our current technology? This is not a wild speculation. The universe is vast, and our instruments, while powerful, are still limited. We scan the sky in slivers, and the cosmos has many places to hide. Brown dwarfs and rogue planets remain difficult to detect unless they emit or reflect significant energy. Nemesis, if it exists, might be lurking at the limits of our resolution, just beyond where we know to look. And what if Nemesis is something even stranger? Perhaps it is not a star or planet at all, but a more exotic object. A primordial black hole, born shortly after the Big Bang, could be massive enough to influence cometary orbits yet small enough to evade direct detection. Some theorists have floated this idea, not just in connection with Nemesis but also as a candidate for dark matter. If such a black hole exists and is gravitationally bound to our Sun, then it could explain many anomalies, from Oort cloud dynamics to potential shifts in long-period comet trajectories. It's important to note, however, that the Nemesis hypothesis is not alone in attempting to explain such mysteries. Other competing ideas, like the galactic plane oscillation hypothesis, suggest that as the solar system passes through the Milky Way's dense midplane every 30 million years or so, it might gravitationally disturb the Oort cloud, triggering comet showers. In this model, the galaxy itself is the agent of change, not a hidden companion. This theory retains the cyclical element of Nemesis but externalizes the cause to galactic tides. It's an elegant alternative and underscores the need for multiscale thinking when contemplating cosmic influences. The beauty of science lies in its willingness to entertain multiple hypotheses, weigh them with evidence, and discard or refine them as needed. Nemesis remains unproven, but it has not been disproven with finality. Its appeal is not just in its scientific implications, but in its narrative potential, a cosmic sibling, a silent partner in the sun's long journey through the galaxy, occasionally sending icy emissaries to remind Earth of its place in the cosmic hierarchy. Ultimately, the allure of Nemesis may stem from our deep, almost subconscious recognition that we are not entirely in control. Our civilizations rise under calm skies, but history reminds us that the heavens have moods. Comets, asteroids, solar flares, and perhaps unseen companions have always had a say in Earth's story. Nemesis, whether real or not, represents the embodiment of that ever-present uncertainty. It reminds us to stay vigilant, to keep looking outward, and to never assume that we have found the final answer. As long as the stars shine and the darkness between them beckons, the mystery of Nemesis will remain a question worth asking, a shadow on the edge of light, daring us to find it. The search for Nemesis is not just an astronomical pursuit, it's a journey into the very heart of how science evolves. The idea of a hidden star lurking in the shadows of our solar system challenges our assumptions, not only about the structure of our cosmic neighborhood but about the dynamics of celestial influence across vast stretches of time. It forces us to confront the fragility of Earth's biological history and the potential role of distant, unseen forces in shaping it. For scientists, this is the very essence of inquiry, an interplay of data, theory, imagination, and humility. One of the most compelling aspects of the Nemesis hypothesis is its ability to unify seemingly unrelated domains. Astronomy, geology, paleontology, climatology, all find themselves drawn into its orbit. Few theories can claim to link mass extinctions on Earth with the orbital mechanics of a companion star. That alone is enough to earn it a place in serious scientific discussion. Even in its speculative form, Nemesis serves as a nexus, a gravitational anchor pulling together disparate strands of evidence and curiosity from across disciplines. The mathematical modeling required to support or refute Nemesis is highly complex. It involves simulations of orbital dynamics over hundreds of millions of years, taking into account gravitational interactions with not only the Sun but also the planets, other stars, and the galactic tide. Even the Oort Cloud, a theoretical shell of icy bodies surrounding the solar system at distances up to a light-year, must be incorporated into these models. This cloud, so far unobserved directly, is believed to be the reservoir from which long-period comets emerge. If Nemesis exists, it would be the perfect candidate to disturb the Oort Cloud, sending these icy projectiles toward the inner solar system and, occasionally, toward Earth. Another curious angle is the degree to which Nemesis might have influenced the very development of life. While extinction events are often seen as destructive, they also clear ecological space, allowing new species to evolve and thrive. The extinction of the dinosaurs, possibly aided by a comet or asteroid impact, paved the way for mammals, and eventually humans, to dominate the planet. If Nemesis is responsible for such periodic cullings, then in a paradoxical sense, it could be considered both a destroyer and a creator. The hand that wipes the slate clean also offers a blank canvas. This duality makes Nemesis a potent symbol of cosmic balance. As our detection tools improve, especially in the realm of infrared astronomy, we continue to narrow the range of plausible hiding spots for Nemesis. The WISE mission's all-sky survey ruled out large brown dwarfs and red dwarfs within a few light years, but it couldn't eliminate smaller, colder, or more exotic objects. With next-generation telescopes like the James Webb Space Telescope now operational, and future missions such as the Nancy Grace Roman Space Telescope on the horizon, the sky will soon be scanned with even greater sensitivity. Each new survey slices another layer off the unknown, and perhaps someday, the shadow of Nemesis, if it exists, will become visible. However, absence of evidence is not evidence of absence. Critics often point to the lack of direct observational support as a fatal flaw in the Nemesis hypothesis, but science often works in reverse. Theoretical constructs guide observational strategies. We didn't detect Neptune because we saw it. We found it because its gravitational influence was inferred from anomalies in Uranus' orbit. The same logic could apply to Nemesis. The unusual patterns in the orbits of some trans-Neptunian objects, for instance, might hint at gravitational shepherding by a distant, massive object, possibly Nemesis, or perhaps the so-called Planet 9. The lines between these hypotheses blur, especially since both propose unseen bodies lurking far beyond Pluto. One possible confusion surrounding Nemesis and Planet 9 is that both are invoked to explain distant gravitational effects in the outer solar system. However, Planet 9 is hypothesized to be a super-Earth or mini-Neptune with a stable, elliptical orbit much closer than Nemesis is presumed to be. While Planet 9 is a solution for orbital clustering in the Kuiper Belt, Nemesis is meant to explain long-period comet showers and extinction cycles. The fact that both ideas coexist in serious scientific discourse speaks to the limits of our current observational capacity. Our ignorance of the solar system's outer boundaries is still immense, and within that darkness, there is plenty of room for more than one mystery. Another fascinating dimension of Nemesis is its potential temporal alignment with the solar system's motion through the Milky Way. As our solar system orbits the galactic center every 225 to 250 million years, it also oscillates above and below the galactic plane. This vertical motion, roughly every 30 million years, brings the solar system into regions of denser stellar populations and potentially stronger gravitational interactions. Some theorists propose that these galactic tides, when combined with a companion star like Nemesis, could produce periodic comet showers. It is the celestial equivalent of tectonic plates grinding together, subtle, slow, and massively consequential. The idea of a dark companion star also raises questions about the limits of stellar formation. Binary star systems are common in the galaxy. By some estimates, more than half of all stars exist in such pairings. So why not the Sun? If our star once had a binary partner, why is it missing now? Could Nemesis be a relic of an earlier cosmic dance, cast outward during the tumultuous early years of the solar system's formation, now orbiting so far away that it barely holds on? Or was it captured later, perhaps pulled from a passing stellar nursery? These questions dive into stellar evolution and the dynamics of early solar system formation, making Nemesis not just an astronomical question but a historical one. From a more speculative standpoint, Nemesis taps into the recurring human theme of the unseen threat. It's a scientific myth, not in the sense of being false, but in the sense of being a story that organizes knowledge and prompts exploration. In that way, it serves a psychological and cultural role, reminding us of our cosmic vulnerability. It says, even in the age of satellites and artificial intelligence, there are things we might have missed, things that could change everything. Technologically, our ability to confirm or rule out Nemesis continues to grow. The upcoming Vera C. Rubin Observatory, with its 10-year legacy survey of space and time, LSST, will vastly improve our capacity to detect slow-moving, dim objects in the outer solar system. It could spot distant brown dwarfs, rogue planets, or even a low-mass star like Nemesis, if it's out there. By observing the same portion of sky repeatedly, LSST can detect motion in objects that would otherwise appear as fixed stars. This capability is crucial for hunting down something like Nemesis, which would move incredibly slowly across the sky due to its distance. The Nemesis hypothesis also has intriguing implications for planetary defense. If periodic comet showers are real, then our understanding of potential cosmic threats must extend beyond just near-Earth asteroids. Long-period comets, originating in the distant reaches of the solar system, are harder to detect and predict, but potentially far more devastating. Understanding what perturbs them into the inner solar system could help refine our models of risk and response. Nemesis, as a theoretical agent of these perturbations, might indirectly help us prepare for threats that are currently invisible. Philosophically, the search for Nemesis underscores the tension between known and unknown. It reminds us that we occupy a tiny sliver of space and time, and that most of what exists is still beyond our reach. The known universe is just a thumbnail sketch of reality. The rest is still in shadow. Whether or not Nemesis exists, the hypothesis drives us to illuminate those shadows, not with certainty, but with curiosity. It is a scientific invitation to stay awake, to keep looking up, and to never be satisfied with what we think we know. The mystery surrounding Nemesis, whether ultimately proven real or imaginary, captures a timeless human urge to explain patterns that are too vast for individual experience, yet too consistent to ignore. The 26 million-year cycle of mass extinctions is not something anyone could witness, but it leaves traces, fossils, craters, elemental anomalies, that whisper of catastrophic upheavals long before humanity walked the earth. If those cataclysms happen with regularity, it suggests a cosmic metronome ticking somewhere far beyond our current perception. Nemesis, in this context, becomes a potential key to unlocking that deeper rhythm of destruction and rebirth, death and evolution. Even without direct observational confirmation, the hypothesis encourages science to sharpen its tools. It urges better telescopes, deeper sky surveys, more advanced simulations, and closer scrutiny of the fossil and geological record. That alone makes it valuable. The discipline of science thrives on ideas that push its boundaries, even if they're later modified or discarded. Nemesis acts as a frontier, a limit condition against which we test the strength and sensitivity of our current understanding. Each attempt to find it, or rule it out, adds data, builds models, and refines our grasp of how the universe really works. There is also a compelling argument to be made about the role of randomness versus determinism in extinction events. If Nemesis exists, and if it truly shepherds comets toward Earth on a predictable schedule, then mass extinctions, once thought to be chaotic accidents, could have a kind of cosmic regularity. That would be a profound shift in perspective. It would mean that some of the greatest turning points in Earth's history weren't just chance asteroid strikes but part of a recurring astronomical mechanism. Life on Earth, then, is not only shaped by its internal evolution but by its celestial environment, by things far beyond its atmosphere or biosphere. This concept also introduces a kind of celestial fatalism. If extinction events are triggered by a distant, undetectable star on a precise but incredibly long orbit, then perhaps our planet is caught in a larger cycle of cosmic reset buttons. But fatalism isn't necessarily negative. Knowing that the universe may have predictable catastrophic triggers also means we could someday anticipate them, and even prepare for them. That changes Nemesis from a doomsday figure into a potential warning system. If we could detect it early enough, perhaps even influence its path or deflect its effects, it would be a revolutionary step in humanity's ability to defend itself against cosmic forces. Furthermore, Nemesis is part of a broader family of cosmic companions and orbital oddities that challenge our conventional models. Alongside Nemesis is the Planet 9 hypothesis, the possibility of primordial black holes lurking in the outskirts of the solar system, and the idea of free-floating rogue planets. All of these concepts share a common thread. Something large and dark might be hiding just beyond our current observational horizon. These aren't just idle theories. They're grounded in gravitational anomalies, clustering of orbital paths, and deviations in expected motions. The universe may be whispering secrets to us through the wobbles and nudges of distant objects, and we're only now learning to listen. The cultural impact of Nemesis shouldn't be understated either. It has captured the imagination of both the scientific community and the public for decades. The very name, Nemesis, drawn from the Greek goddess of retribution, gives it an air of mythic gravitas. This isn't just a celestial body, it's a symbol, an embodiment of the universe's cold impartiality and periodic corrections. Its association with extinction adds a chilling gravity to its legend. It's been the subject of documentaries, books, speculative fiction, and endless debates online and in academic papers. Like all great scientific mysteries, Nemesis transcends pure data and enters the realm of story. In this realm, Nemesis becomes a mirror. What we see in it reflects our own anxieties, hopes, and questions. Are we alone in this corner of the galaxy? Are we safe? How secure is our place in the cosmic order? Is life a stable progression, or a fragile flicker constantly at risk of being snuffed out? These are the questions that lie beneath the surface of the search for Nemesis. They are deeply human questions, rooted not just in curiosity but in existential need. And so we search, not just for a dark star, but for meaning in the silence between the stars. The Oort Cloud itself, Nemesis's presumed target, is a poorly understood and purely theoretical structure, yet it serves as the potential ammunition chamber of cosmic bombardment. The notion that a simple gravitational nudge from a distant star could dislodge thousands of icy comets from the Oort Cloud and aim them toward the inner solar system is sobering. These long-period comets, arriving from vast distances, are unpredictable and dangerous, traveling at tremendous speeds and often going unnoticed until they are already near. If Nemesis is indeed real and responsible for periodically shaking this cloud, it makes it one of the most consequential objects in the cosmos for life on Earth. But what if Nemesis doesn't exist? What if the periodicity in extinction events is an illusion, or the result of geological bias in the fossil record? It's a fair criticism, and one that many scientists have raised. Correlation does not equal causation. Multiple factors, volcanism, plate tectonics, changing sea levels, supernovae, gamma-ray bursts, could all play a role in extinction events, independently or in concert. Maybe we are simply pattern-seeking creatures trying to impose order on a fundamentally chaotic process. In that sense, Nemesis might be a scientific ghost story, an attempt to narrate randomness, to personify entropy. Still, even as a placeholder for the unknown, Nemesis serves a purpose. It pushes science to ask better questions, to improve the resolution of its instruments, and to be open to the possibility that not everything important has been discovered. In that way, Nemesis is not just a possible star. It is a metaphor for everything we might be missing because our tools are still too crude, our models still too incomplete. It stands for the margin of error, the outer edge of knowledge, the dark outline around the known universe that keeps moving outward as we reach for it. In the future, when telescopes like the Vera C. Rubin Observatory begin to catalog faint moving objects across the entire sky with unprecedented depth, we may finally answer some of the questions that have long surrounded the Nemesis hypothesis. We may find no companion star, but instead uncover new populations of distant trans-Neptunian objects, new mechanisms for orbital migration, or even evidence of something stranger, like primordial black holes or ultramassive comets. Or perhaps, in a dramatic twist, we will actually spot Nemesis itself, a cold, dim dwarf star or brown dwarf, orbiting at the very limit of our solar system, faint but undeniable. And if we do, everything will change. Our textbooks will be rewritten. Our models of solar system dynamics will need revision. Our understanding of extinction, planetary defense, and even life's history will evolve. But more importantly, the discovery would reaffirm something deeper, that the universe is still filled with secrets, and that curiosity, humanity's greatest trait, is the torch that keeps us moving forward through the darkness. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.